Hi, everybody. Just make sure I know how this works. All right, good, perfect. Well, thanks for having me. I'm Ryan McDonald. I work at a company called ASAP. We build AI solutions, agentic models for workflow automation. You can ask me about it at the breaks. The first lecture is going to be on classification. We're going to dive into what that is, different models, data preparation, things like that for classification. I've been given some version of this talk, I think since about 2007 at the Swedish Graduate School of Language Technology. Of course, a lot has changed since 2007 in terms of AI, so it's been updated. But I'm fortunate that, I don't know if you can read that, but a number of people have actually taken the slides, updated them, made them better over the years for other summer schools, and I'm grateful that I've been able to take that content and bring it in, but of course, any errors are mine and mine alone. Okay, so I think, do I do that? Perfect. All right, so first, classifiers, classifications. So the lecture is ultimately about a broad set of tasks. So a classifier really is any kind of program that you take some input, whatever that is, and you produce a discrete output that labels that input in some way. So maybe the one that you're most familiar with is the one on the bottom left, which is spam classification. It's kind of one of the oldest classifiers that have been in broad use, commercial use for a while. And the input is an email, it's some text, maybe some images. That's the input. And the output is binary. You either say it is spam or it's not spam. If it is spam, it goes to that folder. If it's not, it goes to your inbox. And I know a lot of people don't use email anymore, but if you do use email, it's so good now you don't even notice it's around. It's that old. But there's a lot of other things. Take a review, try to understand, did that person have a positive feeling towards the place, a negative feeling towards the place or thing. Certainly assistance. Maybe it's done a little bit differently today, but the first sort of virtual assistants that were out there, Alexa, Google Assistant, Siri, they had sort of a triggering phase where we would say something to the phone and it would classify what we're asking the phone to do or telling the phone to do along a set of categories like set an alarm, do some kind of navigation, do a search, ask a question. All of these, and really almost everything that machine learning models do today is some form of classification. So I'll just say up front, there's going to be math, a lot of math actually. It's okay if some of it just might seem pedestrian to you, and that's fine, bear with me. Some of it might seem like a foreign language, and that's also fine. It's actually not important to understand every little thing in the math. I put it in the slides mainly so you can go back and take a look at it and understand it in depth later. The main thing is just to get the broad concepts, like why are we computing that thing that we're computing? Like what is that going to buy us as we're learning these classifiers or doing some kind of inference on these classifiers? Okay, so one thing I will point out is that 2/3 of the lecture is about linear classifiers. And I've gotten the question in the past, why are we focusing on linear classifiers? It's 2004. We use neural networks. Shouldn't we be starting there? But there's a number of reasons to start here. I mean, the first reason actually is that linear classifiers are part of neural networks. The layers of a neural network, a lot of them have properties of linear classifiers. We sometimes just throw functions around them. The prediction, the last layer of neural networks is actually a linear classifier, so it's good to understand those mechanisms in depth. But the nice thing about linear classifiers is that we just understand them. People have been studying them for, I think, 150 years at this point to some degree. So we just understand a lot about what they can do, how to optimize them, the mathematics of them. And so it's good to sort of get into that to some depth because it's a well-grounded problem. And to show you what I mean about that last point on the slide, that linear classifiers are just part of a neural network, we can think of a neural network. You've probably seen a picture like this. You have some input. It's a picture of a dog. Maybe that input is represented by the pixels some representation of the pixels. We pass it through a bunch of layers of a neural network, and we're going to talk about this. I'll talk about the math and how these things work at the last third of the lecture. But the neural network transforms that image through these layers and eventually makes a classification. This is a dog or a cat. So some classifier that tells you, is this picture a dog or is this picture a cat? This last layer is a linear classifier. In all modern neural networks, all neural networks that usually we use commercially, and that this last layer is a neural network, and it's actually one of the most important layers in the network. So studying this and understanding this is important. Linear classifiers ultimately throw out the other layers of a neural network and basically say, okay, we have some input to a classifier. Instead of transforming our inputs with neural networks, we're just going to define what that is by hand, right? So maybe for a picture of a dog, it's just the pixels, or maybe we run some other software that has like edge detection, some kind of segmentation of an image, and we use the output of those classifiers to design the features. But a big part of linear classifiers, or at least how they've been studied in language processing for 20 plus years, is how to define this input, these handcrafted features. And we'll talk about that a bit. So I added this slide this year. What about generative AI? Obviously, ChatGPT broke the dam on a bunch of work that had been happening in the 5 to 10 years before that, and generative AI, just was everywhere all of a sudden. It even surprised me, and I've been doing this for a number of different years. Well, just to point out that, and these are subsequent lectures, so I'm not going to get to this detail or these types of models in this lecture, but transformers, which is the architecture, the neural architecture of basically any large language model that you're using, all the OpenAI ones, all the Anthropic ones, Google, Facebook, whatever. The last layer, again, is a linear classifier here. The thing that predicts what's the next word is a classifier. It's basically saying, of the words I can predict, which is the most likely one that's next. So that is a classification problem. There's also a bunch of linear classifiers in all that bit in the middle. But again, just to point out that A, this is a classification problem, generative AI, and there are linear classifiers in these models, which we're going to talk about. Okay, so classification, we sometimes categorize it in different ways. I think the two most interesting ones or prevalent ones are binary classification. So this is something like spam detection. So this is a case where there's two labels, right? It's spam or it's not spam. And there's a lot of different problems that you can instantiate that way. The next one, and we're going to focus on this one mostly in this lecture, is multi-class classification. And here we're not just saying something is true or false. We're taking a list. It's a finite list, a well-defined list of possible output labels. Here's an example, is topics given a news article. And we want to pick the label, classify that article with the right label here, right? So this is about, AlphaGo, beating the champion of Go. So this is about technology. We add that label, but obviously if it was an article about the UK election, that would be politics or something like that. The reason I'm going to focus on multi-class classification, it makes the math a little bit trickier than the binary case. But of course, if you can do the multi-class case, you can do the binary case. And a lot of the models we're going to be talking about over the week in terms of deep neural networks, language models, things like that, they're all multi-class classifiers, right? Pick one word from a set of possible words. So we'll focus on this, but I will sort of sprinkle in binary classification when there's some interesting aspect of it. All right, so I'm assuming that everybody knows what machine learning is as a broad concept, but maybe hasn't implemented any machine learning algorithms or doesn't know machine learning algorithms themselves. Right? I know there's probably people in here that do know more than that, but I'm going to assume that. And the first thing I want to do is kind of just start with a little exercise, which is kind of a way to show you, get you some intuition. How can machines learn things? How do they learn from data? And so I'm going to do this without language, because, you know, we all speak English, at least here, and we have our biases in that. I'm going to use symbols. So you don't know, this is a language. It's a bunch of symbols. Maybe it's an ancient language. You don't know what it is, right? And I'm going to tell you, I'm going to give you sequences. So these are documents or sentences, who knows. And I'm going to give you labels. So here's binary. I'm going to tell you some of these are labeled -1, and some of these are labeled +1. You don't even know what the labels mean. It's just -1 and +1. Maybe they mean something to the person that wants to build this classifier, but you don't know it. And so you are like the machine at this point, right? The machine, before it begins, it doesn't know what English is. It doesn't know what the output labels are. It just sees a bunch of symbols, right? But it can learn, and we're going to learn here. So we have 4 sequences with 4 labels. I get a new sequence that I haven't seen before. And what label do we think it is? I heard a -1. So that's actually a question. Feel free to shout out. And by the way, feel free to interrupt me, ask questions. If something's not clear, I'll do my best to answer. Don't let something go if it's blocking you in terms of content. It's -1. Why do we think it's -1? Yep, so this is memorization. That's exactly it. There's a lot of other things that could tell us it, but at the end of the day, we've seen exactly this example before in our training data. So all else being equal, it should get the exact same label. What about this other sequence? So here's one where we haven't seen the sequence before. What do you think the label is going to be here? It's going to be -1 again. Why? Whoever said it, I think. Yeah, so that's a good guess. Starts with a star. Well, first of all, stars are more frequent in -1 than +1 examples. That's a good indicator. The hearts only occur in -1 examples. There's also something interesting around the diamond. Does anybody know what it is? It's position. In -1 examples, it only happens in the second position. In +1 examples, it only happens at the first position. And we're going to talk about this a little bit. How do we represent features and what that means? Okay, what about this new sequence? Star, diamond, circle. People think 1. Okay, so why can we do this? I kind of gave you some intuition for why we can do this, right? You know, we look for patterns in the data. We've broken down the data. We say, okay, well, there's symbols. How frequently do those symbols occur? Where do they occur in the sequence? Things like that. And we start to maybe just count what's the most likely thing as the output. And so here's to give you an example. Well, why did we choose label 1 here? This is a modeling assumption. So I'm going to take a modeling assumption here that the probability of a label, -1 or +1, can be decomposed by the symbols that occur in that sequence. And so this is what we often call a bag of words assumption, that the order of the words or where they occur relative to other words or tokens doesn't really matter. So the probability of -1 given star, we just count, and we say, well, it's 67% because 3 of the times I saw a star, 2 of them were in the -1 label, but +1 and star is 0.33. We do that for diamonds. That doesn't really matter. It's 0.5 in both cases. And we do that for hearts. And we see that it's 1 for hearts and 0 for others. And so just looking at this, maybe we sum these probabilities up or we do something else with them to sort of get a single number. But just looking at this, it's pretty clear, okay, it's -1. And I think this is what everybody did. What about this label? So someone said +1. But if we actually make this bag of words assumption, it's hard to differentiate between these two classifiers. They both have the same probability. I see star twice for -1, only once for +1. I see diamond once for -1, but twice for +1. And circle, I just see it once in both cases. So why would someone say +1 here? It's the positions, right? That's one good example. The position of the diamonds is in the right spot for +1. There's a couple other things here. One is the diamond circle. I see those next to each other in the +1s. So if I go beyond a single word and I look at pairs of words or pairs of tokens, then I see that in the +1. I see also star and triangle, not diamond, star and triangle in the together in +1, but I don't see it together in -1. So how we actually think about our inputs and represent our inputs will help us make these classification problems. And we do this all the time. We see patterns. You may not realize you're doing it, but we do it all the time. And this is how machines are going to learn as well. And this is just a simple example. This would be something akin to a model called naive Bayes, where we make some assumptions, we get some data, we do some counting, and then we make classifiers. All right, so ultimately that's it. What is machine learning? It's we define a model of interest. We had a model there, a bag of words model. We just assumed every token or every word in the sequence was independent of each other. So that's the assumption that we're making. It was a conditional model of the output label given the input label. And we fit the model to data, and we fit the model by counting. We just counted the number of examples. So this is kind of the first example of a machine learning model on data. And this model is obviously, it's not as good as a massive neural network, but we use them. Something like this we use for ages, and it can learn things. For instance, spam classifiers, it can be a pretty good spam classifier. Okay, so that's the start. Again, interrupt me. That's just to kind of get you primed for where we're going. But now I'm going to dive into kind of the meat and potatoes, some of the terminology and how we represent features, how we represent that input for language, really sort of treating language as the modality that we're looking at for these tasks. Okay, so some notation. This is going to be important. It's a notation-heavy presentation. And if you forget the notation in future slides, just interrupt me and say like, oh, I forget what Y is or X is, and I'm happy to oblige. So X is going to be some input. That's it. Comes from a space of inputs. That space can be infinite, all the sentences that could possibly ever be written, all the images that could ever be taken, and some output Y. Now we're going to assume that Y is finite for most of the lecture. Again, it doesn't have to be. If we think about a translation, that is a Y. It's a structured translation. I think tomorrow or the day after, we're going to dive into models for not predicting single labels, but sequences of labels. But generally now, let's just assume it's a finite set, and usually a relatively small finite set of things that we're predicting into, like a topic, or it's spam or it's not spam. The notion of an input-output pair is critical, and this is a pair of XY examples. So we know that for a particular input X, an output Y is the true output for that input. And how we get those examples dictates the types of models we might use, and generally we would refer to these things as supervised learning, where we are given those labels as a gold standard, maybe unsupervised learning, where we try to infer them from large amounts of data. We'll get to that in a bit. But basically, the model knows that for an input X and an output Y, that they're coupled. So let me dive into supervised machine learning. So we're just going to assume that we have this labeled data set. Maybe humans have created this data for us. Maybe we've scraped it from the web, whatever that might be. But it's a data set D that is just a bunch of pairs of X and Y. Actually, that is wrong. That should be D. Not the size of the inputs, but the size of the data. And this is going to be the data by which we are going to learn the model. So that would be like those 3 sequences of symbols we saw before with the +-1 label. That's D in this particular case. So our goal is to learn a classifier, call it H, that maps from some inputs, the input space X to the output space Y. Give it an email, tell me if it's spam. And we want to learn it so that it generalizes well to arbitrary inputs. I could just memorize, I could just take a lookup table and take every single input from the training data, put it in a lookup table, and then when I get a new instance, check if it's in the lookup table. If it is, output the result. If it's not, do something arbitrary. That is actually a machine learning model. It's just not a particularly good one. You're just not going to generalize well to things. So then at test time, we have this function h. I'm going to use y prime typically throughout the talk to just mean the prediction of the model. might be the true output, the actual gold output, but it could be incorrect as well. But if we've done our job and we've set up the model in the right way, hopefully when we're deploying this thing in the wild, y prime and yt, so the predicted label and the true label, are basically the same thing. So these types of models, this general framework here, can go by different names. Regression is one. We're not going to talk about that here. I just want to put it out there so you at least can connect the dots here. So regression deals with continuous outputs. So here y is actually not a discrete set, a finite discrete set of things. It's just a real value. So given a news article, how much time will people spend reading it? This might be something that advertisers might want to know when they're placing an ad on a news article. Maybe we want to predict, given an image, some XY coordinates. Is someone going to click on those coordinates, or is there a document at those coordinates? Like what coordinates is the dog at, or something like that? That would be a multivariate regression problem. As I said, this is about classification. Binary classification, we've talked about. Multi-class classification, we've talked about. And then structure classification, you will talk about, but the idea here is y can be exponentially large, so a translation, right? Each position in the output is finite, a vocabulary of words, but the way you put those together, you get combinatorial explosion for an entire sequence, and that is going to require a different set of techniques. We're not going to talk about that today. What about generative AI? Well, as I mentioned with the transformer example here, I just see language models and generative AI as classifiers. You have some context. The input is the prompt, a document that you retrieved, if you're doing some retrieval augmented generation. You put that in together, you sort of concatenate that all together. That's your input, X, and your output is a set of words. What word is going to come next? And you just repeat that process. That is essentially generative AI in a nutshell, and it is a classification problem. All right, so let's move on to feature representation. So we have to take some input X, which is a sentence, let's say, or a document, and I have to represent it in a way that a computer can understand what that means and actually run mathematical operations on that input. And for years, this was what we spent our time doing. Like we did a lot of machine learning and natural language processing, but we thought a lot about data. We still do. Thinking about data is sort of permanent in the life of an NLP researcher. Thinking about outputs is also permanent. But even 10 years ago, we often thought about the representation. How do we take that data and how do we represent it? We still do via things like prompts or word representations, vectors, things like that. But feature engineering was the way we did it before. And it's important to know, and it'll sort of get us on the right path to more modern techniques for representing our inputs. And again, there's a bunch of techniques here. It depends on what you're trying to do and trying to solve in the computation that you have. So we need this representation. I'm going to define phi of x. This is basically going to take x, which is like a word or a sentence or something like that, and is going to map it to a high-dimensional feature representation. Any vector representation of the word, high-dimensional or not. I'll show you an example what that means. This can really be anything. It can be binary features, so 0, 1. That's actually was the most common for many years. It could be categorical features, so just 1, 2, 3, 4, 5. Or it could be a continuous feature, so just any real value as it was. We often focused on binary features that made the math a lot easier, things to compute. We can always convert categorical to binary by just kind of exploding the space a little bit. So that's where I'm going to start, on sparse binary features. So to give an example of this, let's say we have a document X and we want to predict some topic, right? Sports, politics, finance, technology, whatever those topics might be. So phi is my representation. I'm going to take phi of x, and let's say j. Remember, phi is a vector. J is the jth element of that vector. One feature I can define is, well, if x which is a document, contains the word interest, I'm going to fire that feature. I'm going to set it to 1, 0 otherwise. So this is just an indicator feature. It just indicates that in X, I see a word interest or a substring interest. I can also have some real valued features if I want. The percentage of words in X with punctuation. These are two features that you might think would be predictive for understanding finance, right? Like a finance article might have a lot of dollar signs, decimal places, the word interest, or whatever that might be. Another feature that we might do, if you're looking at something like syntactic analysis, predicting whether words are nouns, verbs, adjectives, you might say, okay, well, it's 1 if X ends in the word ed, because in English, if it ends in the letters ed, the suffix ed, it's likely to be a verb. So that's also a predictive, not always, but it increases the probability. So it's a predictive feature. These we just defined. It's not like they were given to us a priori. We didn't know them. We took the task, we took the data, and we defined the set of features that we thought would be useful for prediction. So bag of words we've talked about before in the sort of thought experiment where we just had a bunch of symbols. That is a very common feature representation. So let me show you an example of that with actual language, English here. So let's say X is a name, or X is some string, right? I'm going to define 5 features here. The first feature basically just tells me George is in that string I'm looking at. X is a string here. The second feature, Washington. The third feature, bridge. The fourth feature, general. And then I have this kind of special fifth feature that just tells me, well, if there's a word in X that I haven't seen before. This is useful for a lot of reasons. We call this unknown word feature. But if there's some feature that's just new to me, because we have to define these features beforehand, they have to be static and fixed, but sometimes at test time, I'll see something that I haven't seen, let's say in my training data or before. So how would I map this to a feature vector? General George Washington is pretty easy. I see general, which is the fourth feature, so I set 1 here. George Washington are the first 2 features. I set it there. George Washington Bridge is also quite easy. The first 3 features are on, right? George Washington Bridge, 1, 2, 3. The others are 0. George Washington University, well, George Washington here. University I haven't seen before. It's not in my vocabulary, which is essentially these 4 known words here. So I fire on the unknown word. George of the jungle. One thing about bag of words is often we don't care how many times a word occurs, but that's an assumption that you can get rid of. That's not necessarily, that's not necessary, as I should say, but we're going to make it here. George, we'll just fire 1. These are binary sparse features. We just saw George, doesn't matter how many times we saw it. Of the jungle, all of those words are unknown, so we're just going to fire the unknown feature once. So this is feature representations, how we define them. This is going to be the way we're going to take inputs and create mathematical representations, numeric representations that a computer can actually operate over. As I mentioned, this was what we did for years and years and years. And actually, the way NLP pipelines worked, we would often define features, create classifiers, use the output of those classifiers as features for other classifiers down the road. So we would stack a lot of classifiers together. And I spent years doing that at a large search company. A good example might be, well, I want a classifier for part-of-speech tags. I'm going to use those outputs to predict named entities. So named entities is a string, a person, a location, a place, location, place, a thing, an object, a geopolitical entity, things like that. And then I'm going to use that to make a classification. So part-of-speech, maybe understand Google noun versus Google verb, like you should Google it versus Google is a search company or something like that, right? Knowing that distinction, you make that part-of-speech tag. If I know that part-of-speech tag, it's going to tell me more, am I talking about an actual entity? So the verb's not an entity, but even what type of entity that might be. And then entities can help us with topic classification, right? So which George Washington are we talking about? Are we talking about the person? The historical person? Are we talking about a bridge, which is a location, or some geopolitical, well, I guess what's a university? It's some kind of organization, anyways, however you want to categorize it. Okay, let's keep pushing. All right, we're going to assume multi-class classification. Well, actually, maybe this is a good place to stop and see. Are there any questions? Everything clear? Don't be shy. Okay, I'm just gonna trust you. Right, so we're going to assume multi-class classification. Right, some input. There's a set of labels we want to predict. That label set Y is finite, and we're going to go from there. So linear classifiers. Let's actually dive into what a model looks like. So linear classifiers are parameterized by a weight vector. We often talk about weights or parameters for the features. We'll call this W. W is going to be important in the future. And there's going to be lots of W's. So let's give an example. Let's say the dimension of our inputs is 5. So we have our feature vector dimension, which is 5. And let's say this is our parameter vector here, weight vector here. It has to be the same dimension as our feature representations. So yeah, that's what that says. We're actually going to need not just a single weight vector. We're going to need a weight vector for every single possible label. These weight vectors, the intuitions here, is they're going to tell us, they're going to give us parameters that will tell us for every single label, what is the score or probability of that label. So that's what we're going to learn. That's what they're going to represent. These are the things that are going to actually help us classify what is the true output label or what we think is the true output label. So this is an important concept that we'll use throughout the lecture. We have WY is a weight parameter vector for some label Y. We're going to use script of W to mean the concatenation of all these weight vectors, right? So we have a weight vector per label, and I'm going to give you an example to get some intuition of this. We have a weight vector 1 through the set of labels. We concatenate those all together. This is kind of a notational nicety that's going to allow us to make the math a bit shorter, but it's actually critical to know. So very simple. Let's say we have 3 labels, 1, 2, 3. The first weight vector is 1, 1. Second weight vector is 2, 2. Third is 3, 3. The concatenation is 1, 1, 2, 2, 3, 3. So nothing magic there. That's all we're doing. All right, so in linear classifiers, the score or probability or however you want to set this up, the main thing is that it's a linear combination of weights and their features. What does that mean? So at test time, we want to get the class Y prime, so what we think the prediction that maximizes this score. Just the dot product between the weight vector for Y and the feature representation X, and we want to find the Y of all the Y's in our output set, or let's say our topic set in this case, that has the maximum score. That's our prediction, right? So you iterate over every single topic. Let's say we're doing topic classification with the document. We compute the document feature representation. We use the weight vector for that particular topic. We do this dot product here, this linear sum of features and weights. That gives us a real value. We'll call it a score, typically. And we just find the topic that has the highest score. And that's our classifier. And linear classifiers, this is kind of at their crux. This is really what's common about a lot of them. And this is just the dot product. So just sort of the piecewise multiplication and sum of the elements. How we get these weights is different machine learning algorithms have different assumptions and optimization procedures for getting these weights. But at the end of the day, once they have the weights, they're identical. They're the same thing. So to ground this a bit, just so you have a end-to-end example, dimensions 5. Let's say we have 2 labels, person, location. So we want to understand, is a string a person or a location? We'll say the parameter vector for person is this parameter vector here. The parameter vector or weight vector for location is this one here. And I get an input, X, which is George Washington Bridge. I take that, I pass it through my feature map. I get my binary feature representation here. And then basically I say Y prime is the argmax of, over these 2 labels, location and person, of the dot product. Just blowing that out here, it's going to be the argmax between this set, which is the dot product of the location weight vector times by the feature representation, the person weight vector times by the feature representation. So this is two numbers here. This is a set with a comma here. Just computing those, right? Minus 0.6 times 1 is minus 0.6, plus 2.4 is 1.8, plus 4 is 5.8. And then these two numbers don't matter because there's zeros over there. So we just multiply them, they disappear. And we get 5.8. That's how we get the score for the location. And we get that for all our class labels, and we say, okay, which is the best one? Location has the highest score, so George Washington Bridge is a location. That is a very basic but full example of what a linear classifier might be. Of course, where these weights come from, that's kind of the crux of it. How do we get these parameters that will allow us to make those classifications? There's a key thing called a bias term. This by here, you have one for every single label. We often talk about that in the context of linear classifiers. The idea here, the intuition here, is some outputs might be much more frequent than others. Let's say in news articles, I would say people names are much more frequent than organization names. I think that's true. I'm not sure, but there are often class imbalances like this. For instance, in spam detection, well, I don't know if it's true now, but at one point historically, most of your email was not spam. So there was an imbalance this way. This allows the model to learn that. All else being equal, I have a bias. Should I predict it one way or another? If I see George Washington, I'm actually not American, I'm Canadian, but I lived in North America for many different years. If I hear George Washington, I have a bias to the person. I don't have a bias to the bridge, that's for sure. I definitely don't have a bias to the university. So that's probably simply the documents I've read over my life. I have that bias, and all else being equal, I'm just going to assume someone's talking about George Washington, the person. This is a bias term that allows us to do it. Fortunately, we often don't have to worry about it. We just fold it in. We just say, okay, take our feature representation, add a single one there that's always on no matter what. And since we're multiplying that by a weight vector specific to a label, we're just going to get that bias term anyways. But you'll see in a lot of the papers and textbooks you read, this is kind of a common way to write it. I like to drop it when possible. Now, talking about neural networks, just briefly, before we move on, there's another way to represent linear classifiers. We basically say we have this weight matrix W here. The rows are these weight vectors per class, and we just stack them on top of each other. We take our feature vector phi of x here, we transpose it so that we can do a proper matrix multiplication, and our bias terms here, one per label, and we just run this computation. So this will give us a vector that's of the dimension of the output labels. So this is essentially a score per output label. And this will give us the bias terms that we can add into it. So you'll see this representation when people talk about neural networks all the time. But this is just a linear classifier representation. When we get to neural networks, I will switch over to this. And I'll actually show you why this is true later in the talk. But just to point out, what I'm talking about and the way I'm representing it for linear classifiers is equivalent to this representation here. It's transposed. So I think of the feature vector or the weight vector as being a horizontal version. Transpose is just flip it on its side. Yeah. Okay. Another interesting point to notice, you don't have to necessarily remember this, but with binary labels, we can simplify classification. So when you have a binary classifier, we can take our typical multi-class classifier here. We can say, well, that's equivalent to basically saying, I'm going to predict +1 if the score of the +1 class, which is this one on the left, is greater than the score of the -1 class, right? I mean, that's our argmax rule. That's just how we've defined it. So if that score is greater, I'm going to say +1, otherwise -1. Of course, there's the special case where they're equivalent. I'm not just going to ignore that for now. You can sort of arbitrarily decide ties if you want. Moving around some math, so basically moving this term to the left of the inequality, I get this. So if the score of the true class, or +1, is minus the score of the -1 class is greater than 0, I'm going to predict +1. I move the weight vectors around. I just do a little bit of arithmetic, and I get this representation here. You can do it yourself. And what I can see is that actually I can just reparameterize this. I say, well, I don't have 2 weight vectors here, since if I subtract one weight vector from another, I just get another vector of the same dimension. So I just say, well, I'm just going to call that V, whatever that is. In the bias term, I'm just going to call C. So now I have a new classifier that says, just take the sign of this vector times by the feature representation plus C. So I only need half the parameters. So in the binary classifier case, we sometimes don't keep 2 weight vectors, 1 per class. We just keep 1, and it's equivalent. Again, I'm giving this to you because you will read papers and look at textbooks where they often kind of assume this. They start from the binary classifier case, and it's good to know this. It's good to kind of visually see what this means. So you might also see things like this, where we have positive examples down here. So we have some space. It's a 2-dimensional space here. Positive examples here, negative examples here. This classifier, parameter vector v or w, whatever, and the bias term c, this defines essentially a hyperplane that divides all points. So you can think of, you put your points in some space, and there's going to be a plane. In linear classifiers, there's a plane that divides those points. Everything on one side of the plane is one class, and everything on the other side of the plane is another class. And this is useful because that's going to give us some intuition about how we might want to create machine learning algorithms. If you think about multi-class classification, you can just think of it as sort of the intersection of multiple planes defining different regions of space. Some regions of space are, positive, negative, or circle category here. Another notion which is very important in machine learning theory is the idea of separable or non-separable. So we have our data, we create a feature representation, you can project that into some geometric space, like a Euclidean space, and you can then say, is there a plane, does a plane even exist that can perfectly classify those examples, right? That's, in practice, almost never true, right? Our data is not that clean. But for some theory, it's actually a good concept to have. Usually we get things like this, where I can't rotate this plane or find anywhere to sort of slice the data to get a perfect classification. It's often even much noisier than this. This is not even such a bad example here. All right, so let's get on to learning. How am I doing here? I think I'm good on time. So those are linear classifiers. Everything you need to know about a linear classifier, well, that's not true, but a good chunk of what you need to know about linear classifier were in the slides before. The main thing is, where do these weights come from, right? If I have the weights, I sit down and I define some features. I can build a classifier that's going to make a prediction given some input, transform it to my feature representation. For every single possible output, compute the score with my weight vector, pick the best one. There's my classifier. But where do the weights come from? And for years, these weights were potentially hand-tuned, right? Someone sat down, maybe we didn't have a lot of features, and they said, oh, that seems like a good feature. I'm going to just put a weight there, high weight there. That seems like negatively correlated. I'll give it a negative weight or something like that. That's only going to work on a small set of features, and it's hard to keep track of. It's hard for humans to do this sort of task. We tend to work in very large feature spaces as computer scientists. So the only way to do that is more automatically. And the best way to do things is using data. Don't do it arbitrarily, use data. So we're going to learn these weights. If you remember, script W is the set of all weights. And then we might have a W, which is a set of weights for a single output. And we're going to use our training set D to do this. And that's going to be the next chunk of the lecture here. So let me start with perceptron. How many people have heard of perceptron? Oh, good. So I don't have to do this. Perfect. Okay, so it's very old. It's very old. And it's wasn't the first AI machine learning algorithm ever written. but it's probably the longest lasting one at this point. It's probably the first that we could actually say something principled about, that we could look at it and understand it principally. So it was invented in 57. Here's all these facts about it. I don't even know what a potentiometer is. I don't know if anybody else here knows. I think it's some kind of like magnetic rotation device or something that like current flows through, so we can do like binary calculations. But that's how old it is. Anyways, that's all I wanted to show here. But it's an algorithm that, given some data, will learn some weights. That's the most important thing. It was in the news. I can see there's a wide range of age groups here. For those who have been around, know that this is a very hyped up period in artificial intelligence. It's in the news all the time. People that I know personally are in news articles, which is very weird as well. And it's for good reason. The strides in the last 5 years in artificial intelligence has just been tremendous, right? I don't know what other people who have been in the field think, but I knew we'd get here some point. I didn't think we'd be here at this point. If you'd asked me 10 years ago, I would have said we'd be here in 20 or 30 years. So the field's just gone. And not only that, I say hype, but it's not hype in the sense like it's vapor or that. There's real outcomes happening, right? In the medical space, in information space, whatever that might be. You can see businesses are doing well and a lot of things are being made. But it is important to point out that we have also been in periods of hype before, and post-war 1950s was one example. I wasn't there at the time, but we've heard stories that people thought translation would be solved in 5 years, things like that back in the 50s, and obviously now we know that was not remotely the case. If you asked me when I was working at Google and I saw a Waymo car drive around maybe in the year 2009 or 10, I would have said that's great. My next car I'm not going to have to drive myself. But now, 10, 15 years later, it's just starting to work, like at this point. Sometimes it's hard to predict, when these things are going to take off. And certainly there were AI winters, and this is one good example, where things just didn't pan out the way people they saw a quick amount of progress and it just didn't pan out. And then people disinvested from AI. I don't think we're there this time around, but we'll see. This is more just history for you. Okay, so perceptron algorithm. It's an online algorithm, or we call these stochastic algorithms as well, but the idea is it's going to process one data point at each round. So it's not going to look at the whole data set at each time. It's just going to take a single instance, training data instance from that set, and it's just going to have a very simple update rule. It's going to say if the prediction is correct, so I'm going to run my classifier. I have a set of weights already. I'm going to run that classifier. If it's right, I'm going to do nothing. I'm just going to leave the weights as they are. And if it's incorrect, I'm going to take the feature representation. I'm going to add it to the weights for the correct label and subtract it from the weights of the incorrect label. I'll give you an intuition maybe why that works. So this is the algorithm itself here. So assuming that I've defined phi of x, so I've defined my feature representation for an input. Really, if you sit down and you implement the perceptron, it is only about 15 lines of code. It's really not a lot of code. I don't know, is that what the lab is today, or maybe? No, okay. But after seeing this, if you haven't done it yourself already, it should be a pretty simple task to do. I've probably implemented it 50 times in my life. But we say, okay, our weight vector here, we're just going to initialize it to 0. It can be random. It doesn't matter. Which, by that, what I mean is the weight vector for every output class y is 0. We're going to keep a counter k. Now, for every single iteration, first set k plus 1 to k. So we just want to kind of keep the weights going. Take an example. So this is the online nature. So observe an example from our data set. Make a prediction. So this is just the classifier label we have now. So now we have two y's. We have y prime, which is what the current weights think the correct label is, and yt, which is the true label. If y prime doesn't equal yt, so if we made a mistake, we're going to do this update. If we didn't, we do nothing, as I said before. But if we did, we're going to do this update. All that is the k+1 feature, or weights. For the correct label, we're going to add the feature representation to those weights. And for the incorrect label, we're going to subtract them. Now, what is the intuition here? The score is a dot product between the weights and the feature representation. If you think about your math, you essentially get something that's proportional to the angle between those two vectors there when you take that dot product. By putting features of the feature representation of x and the true weight label, we're essentially pushing that angle closer and smaller together. So we're essentially increasing the dot product that we're going to get when we do the score. And the same, if we take the feature representation and an incorrect label and we subtract them, we're essentially moving them far apart, right? So this is kind of the intuition here. We're moving weight towards the correct label so that we get a higher dot product at the end of the day. So that's it. It's a very simple algorithm. Just a little bit of theory here, and this is why I still like to present the perceptron. Actually, we do use the perceptron every day. We just don't necessarily think that we're using it. It's kind of a beautiful algorithm. It's simple, but not only is it simple, we can say very specific things about it. So if the data is linearly separable, so if the training data is linearly separable, if you remember what that means is there exists a hyperplane, there exists a set of weights that I can perfectly classify that data, right? So if that exists, and some other things like define some u of primes with a norm, a unit u of prime, right? So the norm is 1, that's not that important. So it's linear separable with a margin y, which we define as being that there is some u of y that separates that data perfectly, meaning it will classify the correct label greater than all incorrect labels with some margin, with some score margin, numeric margin by gamma. The radius of the data, don't worry about. I don't want to get into that. But the idea is, if we make those assumptions, that it's linear separable by some margin, there's a very old algorithm that tells us that we're guaranteed to find a hyperplane. Not the best, but some hyperplane, some way of dividing the data and getting a perfect score on that specific data in a finite amount of time. I used to go over this proof when I gave other versions of this lecture. I'm not going to do it now. There's a paper here in the slides. You can click on it that has a very simple, and the nice thing, this proof itself is also very elegant. It's only about maybe 10 lines or something like that. But this is sort of, the first foray into learning theory, where we've made assumptions about a model. How do we represent the features? How do the updates look? And we can say something precise about the model. And this is critical. And sometimes, depending on the assumptions we make, it's easier or harder to say things. But this is an old example that's quite plain and beautiful. So what can a simple perceptron do and not do? And this is true for all linear classifiers. Well, this is also an old result. So if I have an OR function, so OR is true, which is triangle, if x2 or x1 equals 1, or either of them equals 1, right? And 0 otherwise, false otherwise. I can separate that data, that's fine. And there's other functions, and if I take the negation of x1 and x2, the negation of x2 but not x1, and you plot these out, that's fine. I can find a separating hyperplane to separate this data. So in a two-dimensional space, with very simple functions, perceptron can learn those functions. However, it can't learn other simple functions like XOR, right? So when x1 is true and x2 is true in XOR, that's false. So this position in the top right here is false. You can't draw a line and perfectly classify this data. So this is not separable. So perceptron, is powerful and it's been used in a bunch of different things, but it can't actually solve this problem. But the way we get around it is we change representations. So I'm going to leave this to you, but you can say XOR of x1, x2 equals XOR of these two ANDs. You can map out the 4 different values and check that you get the exact same result, so that's equivalent. The key thing here is that when x1 and x2 are true, that's undefined. That can't be both true for this function and this function. So we've transformed our space. We've taken our representation and we've transformed it in somehow, so we have an equivalent function, but a learnable one. Sorry, equivalent representation, but a learnable one. You can draw a line and classify that here. This is old. People have known this a long time, but I think it gives you the intuition that a lot of what we do in modern machine learning is transforming our data. And whether that's through defining features, through defining prompts, or passing them through multiple layers of a neural network, what we're doing is taking some representation of the data and transforming it in a way that should be easier for the model to learn, gives the model more power to learn. So this is sort of ever present in everything we do, and this is kind of the first example of something that would work. All right, so why am I telling you the perceptron? Is it any good? Well, actually, it was basically state-of-the-art for many years. There was SVMs, logistic regression, other classifiers that were around. I'm going to talk about them next. But in any kind of task that we ran, the perceptron, if it wasn't the best, it was in the neighborhood. It was in the ballpark. And as a result, due to its insane simplicity, it was in tons of papers. Company I worked for, it was everywhere because it was just easy to implement, easy to maintain and understand. Of course, things changed about 10 years ago when neural networks really became practical to use. But up until that point, perceptron, I don't know if it was the most used algorithm, but it was definitely up there. And even for simple tasks today, not the kind of reasoning tasks that you might use an LLM for, but something like a spam classifier, you could probably get a long way with a perceptron algorithm. Okay, let me dive into logistic regression. I think I'm doing well on time here. All right. Again, interrupt. Okay, so it's a little bit more complicated, logistic regression. This is going to be a bunch of math here. Don't worry about it. If you don't get every little bit, that's not important. The main thing is to get the broad concepts. So just try to understand why we're computing something. And if you feel you've got a good intuition for that, then I think you're all set. You can just go back and look at the slides later. So perceptron just dealt with dot products, scores. Take the dot product of a feature representation with a weight vector, parameter vector for some output. We're going to talk about probabilities here. The way we're going to do that is we're going to take that score from perceptron, or that linear classifier score. We're going to exponentiate it and normalize it. The normalization term, z of x here, is simply the sum over all labels, the score of that label, right? So that's a normalization term. The reason we're going to do this, we want a probability distribution. It's a linear classifier. The reason we do this kind of exponentiated thing is it makes it a distribution. First of all, the probability of y given x is greater than 0 for all y's. The exponent buys us that. And the normalization term makes sure that the sum over all possible outputs, probability of those outputs, is 1. So we get an actual probability distribution here. So that's why we do that. There's possibly other mathematical reasons we do it, but broad strokes, that's it. This is often called the softmax transformation in neural networks. You've maybe seen that in different places. The last layer, we do a softmax or something like that. That's all this is. And I would say this is the last layer of almost every neural network you might use today. So this is actually the last layer, logistic regression. So we'll dive into that. It's still a linear classifier, right? Even though we've made it into a probability distribution at inference time, I want the highest scoring output given this probability. I write that out. Well, the normalization term is independent of y. It sums over all y, so it's going to be the same no matter what our y is. We can throw that out. We just get the exponential function, and then these are monotonic. Whatever is maximum here in this score is going to be maximum in the exponential, so we can just throw out the exponential and we get this function here. So it's a linear classifier. At test time, we're going to run inference in the same way we would have the perceptron, or any linear classifier for that matter. Okay, so this is our probability distribution. I'm going to write a little w here that I sometimes use to say with respect to some model parameters we're going to learn, right? These ones here. It's a notational convenience. Just reminding you that script w is just the concatenation or the set of all the weights that we care about, right? One weight vector for every single label. Right, how do we learn w? And now we're getting into something which we call loss functions. And it turns out that there is a loss function for perceptron, even though we don't think about it as optimizing one. But with logistic regression and neural networks and support vector machines, there is an explicit loss function that we're optimizing. And this goes by many names, but we're going to say it's the log likelihood, the conditional log likelihood, the negative conditional log likelihood. It doesn't really matter. Actually, the crux of it is this term here. What we want to maximize is we want to find some weights, script w here, that put maximal probability on the true output label given input x of t. That's what we want to multiply. So this product here is going to be optimized, maximized, when our weights give probability 1 to the true output and 0 to all other outputs, right? So that's a great output. And you know, in separability, we've separated the data. If we've done more than separate the data at that point, we've put all the mass of the classifier on a single output label. I'm going to take the log of that. That's a mathematical convenience. I'm going to take the negative of that. People do it because we tend to think of optimizing convex functions, but you know, it's identical. But let's keep that negative there. The reason I do the log is it allows me to sort of plop it through this product, and then I get a summation. It's a lot easier to sometimes compute things with summations as opposed to products, especially the kinds of computations we're going to look at. And if I write this out, I get this function here. So I'm going to simplify it a little bit, right? So the log of this distribution is the log of the probability is the log of the numerator minus the log of the denominator. I'm going to move the negation in, so I'm going to get the log of the denominator. That's all that is. That's the definition of z of x, minus the log of the numerator, and the log of an exponential, they cancel each other out. I just get my linear classifier here. So what I'm saying here is basically set my weights to assign as much probability mass to the true score, right? Because if I make this as high as possible, and since I'm subtracting it, I'm going to minimize this whole function. And as small mass as possible to the whole set of labels. Now, the true label is included in the summation, right? So that might seem a little counterintuitive. Maybe I only want the negative labels in that summation. But since it is a probability distribution, every time I put mass here, I'm necessarily taking away mass from the other labels. So there is kind of a constraint there that allows this optimization to work. Okay. This objective function is convex. There's a local minimum. It's also differentiable, so we can use a number of different techniques to solve it. There's no closed form solution. We can't just write out some math and solve it. We have to use some iterative techniques to find the solution. And so let's go over one of those. Right, it's convex. There's a guarantee of a global minimum, right? There's only one stationary point in this function, and it's the optimal point. A useful concept, many of you may know this, I don't, many of you may have learned it years ago in a calculus class and don't remember it so much. We're going to talk about the gradient of a function with respect to some parameters w. This is just the partial derivative of that same function, a vector of the partial derivatives of that same function with respect to every single weight, every single individual parameter itself. We want to compute the gradient. The gradient is essentially it's the vector that is the direction and fastest rate of increase for a function at the point that we're computing it at. There's a couple properties about the gradient. First of all, that's useful. It's going to be useful for optimization. We know the right way to go when optimizing this function. But also, we're going to know something about whether we've optimized the function or not. If I have some weights and I compute the gradient, if the gradient is 0, by definition, we're at a stationary point, and we'll know that we've actually optimized the function. So if I find the weight vector, W script, where the gradient is 0, then I've optimized the function. There is a whole slew of literature. People have spent their entire careers thinking about optimization, convex optimization even, which is a small set of full optimization. So I won't do it justice here. We typically use iterative descent methods in machine learning to solve these problems. In particular, we use gradient descent methods. Gradient descent is very simple. That's why we use it. You take a weight vector at k plus 1, and you update it. You say it's equal to the weight vector at the last iteration. So we're going to constantly be updating these weight vectors, minus some step size. Step size is important here. The gradient of that function with respect to the parameters at the last step. And gradient descent essentially finds the gradient will point you to the steepest, fastest way to get to the optimum. And so you just take that step every single time. One key here is this step size. How big are you going to go, right? I could have gone in this direction, but taken a step size over here, and that's not going to help me, right? I'm not going to be at the minimum. So a lot of the learning theory around gradient descent is, how do these steps look? Are there any rules of thumbs or any principled things we can do on the step size? I'm not going to dive into it here. I think one rule of thumb, at least for theory, is on every step, if the step size is exponentially decreasing, you can usually prove that gradient descent is going to work. It's going to find the global optima. In practice, that would be too slow. So in practice, we have better rules than that. Fortunately, nowadays, we have things like Hugging Face and PyTorch where we just say optimize or train, and all of this is kind of done for us behind the hood, but this is what's happening behind the hood, and those tools have actually implemented decent strategies for step size, usually data-driven as well. Okay, so gradient descent for logistic regression. This is our loss function. If you remember, we wanted to minimize this. This is for a single instance. We want to minimize this for all the training examples, right? We want to have the score of the correct label as big as possible and the scores of the normalization term to be as small as possible, right? So put all the mass on the correct label, right? This is a loss function. We're going to minimize this loss function over our data set here, which is really finding the argmin over all the points, that loss function. And loss function is kind of a key concept that we're going to talk about. It's the loss with respect to some parameters for a single instance or an entire data set. It depends. And this loss function here, I called it log loss, conditional log loss. It also goes by a term cross entropy. So when you say I'm going to use cross entropy in a paper for neural networks as my loss function, you're doing log loss. They're actually equivalent. I'm using the older term here. But let's say I can compute this, right? So let's say I know this, and let's say I can compute the gradient of this. The updates are going to look like this. At k plus 1, it's equal to the weights at k minus my step size, the gradient of my full function here, my full thing I want to minimize, which is the sum over all training instances, the loss, this thing here, of that instance. I'm going to pull out the sum because you can do that with gradients. They're decomposable that way. The gradient of a sum is just the gradient of the individual components. And so that's what my update looks like. And so basically, this is what I need to compute. If I can compute the gradient of this loss function, then I can train a logistic regression classifier, and I can find the global minimum. So we call this a batch optimization. because we're actually taking the gradient with respect to all the training instances at once. So if you remember in Perceptron, we took a single instance and we made an update for a single instance. We call that an online algorithm. They also go by the name of stochastic. And gradient descent, this is also true. And in practice, we use stochastic algorithms. We don't optimize with respect to the entire training data. And there's a lot of reasons we might do that. I'll mention them in a second. But SGD is very much like Perceptron. We pick an XT randomly. I mean, that's how we write it in papers. Usually we just sort of pick the next one in the sequence. And then we're going to make a weight update, which is identical before, but instead of summing over all the instances in the training set, we're just going to use a single instance in the training set. So it's kind of in the same nature as Perceptron at a broad strokes, the algorithm. And you can sort of seeing this as, well, we're going to approximate what the full batch gradient is with a single example, like a noisy example. That's one way of thinking about that. And actually, again, you can prove this will converge. At some point, you're going to get the optimum. So this is a perfectly good algorithm to do. We use this for a couple of reasons. It's often faster. We're taking more steps, so we're getting quicker to where we want to be. And sometimes the compute is easier. Maybe it's going to take a long time or a lot of memory to compute for a whole huge data set by doing a single instance at a time. It's just a little easier to manage. It's important to note that there's a spectrum here. I can use all my training instances to compute the gradient. I can use one, or I can use somewhere in between, 5, 6, 12. These are called mini batches. So it's not full batch, it's a smaller batch. So we're making updates based on smaller batches. And actually, that's what a neural network would do. And it's usually tied to the type of architecture you're using. How many instances can I get in a single core of a GPU or something like that? And that will be your batch size, which will optimize your computation and make things fast. But that's how these optimizations are working. And then there's other things here, which I'm not going to go into, which is important in practice. For instance, distributed training. Sometimes my data set's huge. Maybe I'm learning a language model over the Common Crawl or something like that. I can't run that on a single computer. I need lots of computers to do that fast. How do I distribute the gradient computation and make it faster, but also make it principled and work? There's tons of literature on this. It's a very rich tapestry of things. When you do run like a Hugging Face train or something like that, it's not running this vanilla gradient set. I actually don't know what it's running. There's probably even, that's configurable itself, something like Atom or another sort of more souped up version of gradient descent. But at the core, that optimization, the way it's learning its parameters, is a gradient descent type algorithm. Okay, so what does the algorithm look like? It's going to look a lot like the Perceptron. We need step sizes as input here as well, right? There is this extra hyperparameter that we call it. What's the step size for every single iteration? We again set the weights to 0. We initialize this counter, observe an example, and make an update. Here we're always making updates. We don't actually check if the current classifier is good or not. We just always take this gradient, and we go until stopping criterion. The stopping criteria is usually something like the gradient is very small. You can say we're going to stop when the gradient is 0. That means that you've actually optimized the function. You're at the minimum. But it's usually really hard to get there because there's numerical issues and everything to actually, in a very complex function, high dimensional function, to actually get to the point where the gradient is 0. So we usually take the norm of the gradient or something else just to sort of say okay, the gradient is sufficiently small now, that's where I'm going to stop. Or we just say for a certain number of iterations. There's a lot of different reasons for that. And that's why we don't really need to worry about checking if the prediction is correct. If the prediction is correct, the gradient's going to be 0, and we're not going to make an update anyway. So it's kind of equivalent to the Perceptron update there, and we just rely on the stopping criteria to handle that. All right, so computing the gradient. So I'll do this, and then maybe I'll break, because you're probably going to need maybe a bit of a breather after this one. There's a lot of notation. Our loss function here, the log loss, if you remember, is the log of the normalization term, so the mass are the scores that we put on all the labels, minus the score of the true label. This is our loss function here. Remember, script of W is just the concatenation of all of these labels. I'm going to use Y prime to mean some incorrect label. Doesn't matter which one. And I'm going to use Y to mean the true correct label here. Without loss of generalization, I put the position of Y prime on the left of the position of Y, but it doesn't matter. That's just so you can kind of visually see things. Some reminders, calculus reminders. The gradient or the derivative of the log of a function is 1 over that function times by the gradient of that function. Of an exponential, it's the exponential of that function and the gradient of that function. So we're going to use those two facts here. And so I'll apologize for this right now. This is one of those points where don't worry if you don't kind of get the details, just the broad strokes. Why are we computing a gradient? We need this gradient so that we can plug it into the gradient descent model in order to optimize the parameters and optimize that function. But for completeness, I'll go over it. Write the gradient with respect to this function. I'm just going to write that out. That's just the definition of the loss function. I'm going to plop the gradient through the summation here, or the negation, because a gradient of one term minus another is just the gradient of the first term minus the gradient of the second term. Now ignore this part in blue. That's not going to change. Let's look at the part in red. The gradient of a log is 1 over the function in the log, so 1 over the exponential term here, and the gradient of the function. The function here is a summation, so I'm just going to plop that gradient inside the summation, which I can do. That's not a problem. I'm going to notice that this term here is a normalization term. It's just the sum over all labels, the exponentiated score. So I'm just going to rewrite that as 1 divided by z of x. That's just its definition. There's nothing really crazy happening there. I still have the summation over y. The gradient of an exponential function is that function itself times by the gradient of the parameter, which here is the linear score. Moving this constant here with respect to x inside the summation, I get this term here. That term is simply the probability with respect to w, script of w, y prime given x. So that's my probability distribution. So broad strokes, this is the gradient. I've left these two terms here. I haven't actually solved for those two terms. And it's a little tricky to get this conceptually, or at least it is for me. Right, so this is the loss function. Let's look at the partial derivative with respect to some weight w of I, some variable at I. And you remember the gradient is just the vector of all partial derivatives. So I just want to look at one particular value in that gradient. That's what I want to do. So let's look at two cases. The first case, I points to some index in this weight vector here, right? So w of I is part of the weight set for the true output label y. So what does that mean? Well, first of all, with respect to wi, I can ignore, this is just a summation, it's a dot product, right? The derivative of all of these terms is going to be 0, except for one, only the one where I do the dot product between weight of I and the feature representation phi I of x. So I get rid of everything else. Over here, that's also true, but you notice since I is only pointing into the true output label y, all the other terms in this summation for incorrect labels, all those parameters, wi is not in those parameters, right? Because that's only for the true output label. So I can throw out all those terms and only focus on the true output label y, and it's the same. So it'll be probability of y given x times by phi I of x, right? So that's the first case. The second case is I indexes another weight vector, which is not the true weight vector w of y prime here. In that case, the right term here just goes to 0 because w of I is not in w of y. Sorry, w of I and w of y do sound alike phonetically. And so this will just become 0. And as above, the only thing that's left over here is the probability of y prime given x, phi I of x, for the output label y prime that I is pointing into, right? And that's it can be any label. It doesn't really matter. It's whatever I is. So these are our two gradients. And you can see these are going to be 0 when, first of all, I put as little probability as possible on incorrect labels. If I put them to 0, the probability of incorrect labels is 0, then the gradient for this term is going to be 0. And if I put as much probability as possible on my correct label, y, then this is going to be 1, and that means it's just going to be phi I of x minus phi I of x, and we get 0. So you can see even in the gradient, what we're pushing the algorithm to do is to put probability on the correct label, take probability away from all incorrect labels. So what do the updates look like? For the true output y, I'm going to update my weight parameters like this. K plus 1 equals k minus some step size. That's just the gradient that we talked about there. And for y prime does not equal y, so for incorrect labels, the same thing, but for the other gradient for that instance. And this is what the algorithm looks like here. And now it's starting to look a lot like the perceptron algorithm, where we're saying all of this is before, observe an example, put feature representations for the correct label, because this is a negation actually. This is going to come in and become a positive. Add the feature representation for x to the correct label's weight. I mean, there's more going on here than that, but like in broad strokes, you can see that it's actually very similar to the perceptron in that way. And similarly, we're minusing the feature representation for incorrect labels. So that if you squint, you can see the perceptron and logistic regression are doing very similar things. So logistic regression summary, we define a conditional probability, set weights to minimize the conditional log likelihood, find the gradient and run gradient descent. Right, the story so far. I'm going to end here, I think. I think this is the time for the break, if I'm not correct, if I'm correct. And this is what I mentioned here. Logistic regression, maximize the conditional likelihood. We run SGD. We get updates to our parameters that look like this. Again, I moved the negation in, so now I get a positive with the feature vector here. And perceptron is also discriminative, but it's a non-probabilistic classifier. And my feature, my parameter updates, my weight updates look like this. And like I said, if you squint, they look very similar. And actually, there's a way of kind of writing a loss function for perceptron that's somewhat similar to logistic regression. The nice thing about logistic regression is, it's a probabilistic model. It's the loss function is well understood and well used. And by using gradient descent, we know what we're doing. Function optimization. It's a very principled way, grounded way of optimizing the model. And actually, it turns out perceptron is just finding any classifier, any hyperplane that separates the data, that will predict in your training data the right labels. Logistic regression doesn't make such guarantees as that, but what we can see, and I'm going to talk about this in the next section, is it's optimizing something called a soft margin. What it's doing is actually not finding the best, or finding any linear classifier that separates the data, is finding one with the property that it's in the optimal part of space. So it's separating the data by the largest margin that it can find. It's a softmax because it's not actually doing that, but it gets pretty close to that. So there's a lot of principle in logistic regression as well that I'm going to sort of tie together at the start of the next lecture, and then we'll hit neural networks for the last hour or so. All right. So before I get going, any questions, thoughts on the first part of the lecture? I don't think the slides are online yet, but they will be online soonish to take a look at. And you can ping me. You can find me on, I think, LinkedIn or just Google search. You can find me. You can feel free to email me questions or message me about anything. All right, so I want to talk about margin and SVMs before moving on to neural networks. Margin is an interesting property. We already kind of alluded to it a little bit with perceptrons, but for a training set D, the margin of a weight vector is the largest gamma, so this is just a real value, such that the score of the true output, y of t, for an input x of t, minus the score of an incorrect output, y prime, times the feature representation of x of t, is greater than or equal to gamma. So assuming we can find the optimal, or assuming that we can separate the data with a hyperplane, the plane that separates it with the largest gap, margin gamma, that's a margin. And that's what we're often looking for. And this is true for every training instance in our data set and for all incorrect examples, y prime. Oh, sorry. Right, and so why do we care about something like margin? If we look at this example up here, that's some training data. Perceptron might give us a hyperplane like that, a classifier like that, that separates the data, everything's good, it stops. But then at testing time, we see some new instances and we see like, well, actually it wasn't so perfect after all. And actually, if we kind of think about it intuitively, going down the middle makes the most sense, even before we see this example here. And that's because it might be a little bit hard to see here, but the more we move it in the middle, the further this plane is away from different points. And that's essentially the margin, right? How far is the hyperplane away from the points that are closest to it? And intuitively makes sense that we might want to optimize something like that. And it turns out that it's not just intuition that's good. A huge amount of learning theory is based on the fact or supports the fact, I should say, that maximizing the margin of a classifier is good. So there's a ton of literature out there. But in general, a lot of the bounds, and these are generalization bounds, these aren't saying something about your ability to learn the training data. These are saying something about the model's ability to generalize on examples it hasn't seen before. The bound, so this is an error bound. Let's say epsilon is the generalization error. Don't worry about these two values here. The main thing is it's inversely proportional to the margin. So the margin, as the margin gets bigger, the generalization error gets smaller and smaller and smaller. I'm not going to go over that, but this is to kind of back up the fact that maximizing margin just seems like a good idea to do. It's actually, in principle, from learning theory, it is a good thing to do. And just to back up a little bit, Perceptron finds us a hyperparameter, but says nothing about hyperplane, but says nothing about margin. Logistic regression doesn't even guarantee that it separates the data. But as I'm going to show you, it turns out it is doing a margin-like optimization under the hood. But let's look at support vector machines. So this is a machine learning algorithm that was, everywhere for many years. Still, I'm sure, is used in a number of different applications. But it's specifically designed to optimize margin, to maximize the margin of a system. Just a little history. The word support vector, machine support vector, this comes from the fact that the points in the space that are closest to the hyperplane, these are the support vectors. These are the things that ultimately you want to optimize for, right? Actually, all the other points, if we go back, I don't actually need to know in the training data anything about these points here or these points here. I really only need these 5 points here, I think, in order to optimize margin. The rest of it doesn't really matter, what I'm doing. And those are called support vectors. So the way I'm going to present them, we don't talk about it. It's not presented that way, but that's kind of the intuition, and that's where the name comes from. Okay, so let me just jump into what the optimization might be. Literally, we want to maximize the margin. That's the optimization. Now, what does that mean? Well, basically, we want to maximize the margin subject to the constraints that we put up before, that the score of the correct output minus the score of the incorrect output is greater than that margin. So find the value, gamma, the margin, where that's the biggest value, gamma, that this is true, where I can separate the data. Now, so that's it. It's a very simple, declarative optimization technique here. why do I do this? We want to say maximize the margin under the constraint that the norm of the parameter vector W is less than or equal to 1. The reason we're doing this is because if I can find any W that satisfies these constraints for some margin gamma, I can always just scale that W up. I can make it arbitrarily as big as possible and get a bigger and bigger and bigger margin. So that's not useful, so I want to constrain that in a way to box it in and actually just make it a more stable optimization. Okay, so that is the explicit declarative optimization for maximizing margin. We can actually rewrite it, and it's more common to rewrite it as minimizing norm, right? So instead of maximizing the margin subject to the norm of the weight vector being below some value, we're just going to say minimize the norm of the weight vector subject to classifying the instances correctly greater than or equal to 1. So for a fixed margin. So here we're fixing the margin to 1, gamma to 1. We're saying, make sure you classify it, the instances greater than 1, and find the smallest parameters that satisfies those constraints. We're kind of assuming, first of all here, that the data can even be separated, that there is a parameter vector that does classify all the training instances correctly by some margin 1. If that's true, then we should be able to optimize this. This is a little bit easier to optimize, which is why we write this equivalence. And one way to think about it is that, okay, well, reparameterize W, the weight vector, by W prime, which is really the same as, so this is just saying that's the same as W prime norm is equal to W norm divided by gamma. So we're just scaling W prime by gamma, and then we can rewrite it as this. And so basically, what do we want to do here? Oh yeah, so we want to, if we're maximizing this, it's the same as minimizing W prime. Okay, so this is the support vector machine optimization, ultimately. Find the smallest weight vector or weights script W that minimize the norm. This is the norm of the weight vector script of W, subject to the constraints of getting the classifications correct with a score of 1. And the good news is that this is a quadratic programming problem. So there's, again, in optimization theory, there's a whole set of algorithms that are designed just to optimize this. It's still convex, so you can find a global minimum to this problem. And actually, there's off-the-shelf tools, again, that you can use to optimize such algorithms as this. So it can be solved. And there's different techniques to solve it, but that's probably the most common one right now. So what if the data is not separable? What if we can't actually find a set of parameters that classifies the training data perfectly? So there was some work, now it's probably 25 to 30 years old, called slack variables. It's adding slack variables to SVM. The idea here is we introduce this new set of parameters that we're going to minimize over, C of t, right? The intuition of C of t is that the score of the correct output minus the score of the incorrect output is going to be greater than or equal to 1 minus some penalty or some sort of violation of getting that margin correctly, right? These have to be greater than or equal to 0, first of all. But what's going to happen here is if we can separate the data perfectly, think about the case where we can separate the data perfectly, so we can find a classifier that scores the correct label higher than the incorrect labels for all training data. Since we're minimizing this, and C of t has to be greater than or equal to 0, then the optimum is just setting C of t equal to 0. So we don't actually need them because we can separate them. But if we can't, then we can only separate it by some value that's now going to be smaller than 1. And we want to find the smallest C of t's for every single training instance that's true. So we're going to violate our margin when we're optimizing it, but we want to violate it by the smallest amount possible. And that's why we're taking the argmin of this function. So find the smallest violations that you can that will, to the margin, that will satisfy this. And so we get around the fact that it's not separable. And C of t can be actually greater than 1. So there can be instances that we classify incorrectly, and that's fine. In this particular case, we don't require the data to be separable. But the nice thing about this representation is it's still a convex optimization problem. So we added a few variables, and we can still run all the training data before. C here is just the trade-off. It's a trade-off that says, how important is it that I correctly classify all the training instances with a margin, right? And if I make C really big, then I'm going to want to violate the margin as little as possible, because that term's going to dominate the optimization. If I make it 0, it won't matter at that point. Let's rewrite that a bit. I'll just define a new variable lambda, which is 1 over c. I'll multiply the whole function by lambda, and I'll get rid of the c over here. So now I have this function here. This is just a notational convenience. Let's walk through what the support vector machine is doing, another view of doing it. So this is the same optimization as before, minimize the norm plus the slack variables, subject to classifying the correct instance right by a margin of 1 minus the slack variables. I'm going to rewrite that and say, I'm still going to correct, this is identical. So instead of saying it has to be bigger than, the score has to be bigger than 1 minus C of t for all outputs y of prime, I'm just going to take the max, because under this function, if I satisfy the margin for the highest scoring incorrect label, then I satisfy the margin for all other labels, right? As long as I do it for the max, that's fine. So I'm going to rewrite it there, and if I satisfy this, I'm good to go. What I'm going to then do is just rewrite things. This is just arranging things. I'm going to move C of t over and everything else to the end. So I'm going to say C of t has to be greater than or equal to 1 plus the score of the incorrect label, the max incorrect label, minus the score of the true label. So that's just rewriting equivalence. All right, so I just put that up here again. That's nothing new here. Minimize norm of the weight vector and the slack variables subject to these constraints. This is what we call hinge loss. So this is another loss function. We talked about log loss before in cross entropy with logistic regression. Hinge loss is just another type of loss. And what you can see it down here, this is how it's defined. It's the max of 0 or this function here, this score here. And so what that says is that if a set of parameters basically correctly classifies an instance with a margin of 1, then we take a penalty, a loss of C of t. It's 0, right? There's no loss there. We've correctly classified the instance. Otherwise, this is our penalty, right? The margin 1 plus the score of the maximum instance minus the score, or maximum incorrect instance minus the score of the correct instance. We're going to take this penalty here, which is proportional to how bad we scored these instances, right? If this has a very low score and this has a very big score, then this loss is going to be bigger, right? We violated the margin by quite a lot. Right? So I'm going to rewrite this a little bit and say, okay, what the right way of thinking this is essentially a definition of what C of t is, right? It's either 0 or it's this loss function here. And that's equivalent to these constraints here. So I can take my normal optimization there. I'm going to have a hinge loss equivalent where I'm going to say minimize a loss function and a norm. I'm just copying this over here. And the loss function is the hinge loss here, the max of taking a loss 0 if I correctly classify the instance incorrectly or correctly, and this function here if I get it incorrect. So that's quite a lot, actually. So basically what I'm saying is if the parameters classify the instant correctly with the correct margin, so gets the true label with a score higher than all the incorrect labels with a margin of 1, I'm going to take a 0 loss. Otherwise, I'm going to take this loss, which is bigger when I have a small score for the true label, but a big score for some incorrect label. And this is equivalent to the original SVM formulation. Now, the reason that we want to do this seems like we're kind of doing a little bit of like mathematical gymnastics. And why are we doing these gymnastics? The reason we want to do this is we want to get for this lecture at least, want to get the optimization into this form where we have a loss function and we're going to talk about this term over here. And so we're starting to make SVMs look a little bit like logistic regression at this point. We're optimizing for a loss function. The difference is SVMs is this loss function, logistic regression was the log loss. Okay, I'm going to jump back to that in a second, but it's important we talk about regularization, which is ultimately this term over here and what that means. So what is overfitting? So let's stop thinking about SVMs for a second. We have a bunch of data points, and we want to learn a classifier for those data points. If this data points here, which are some quadratic function is what it looks like. If I use a linear function to try to classify these or try to fit them, I'm not going to do such a good job. I can't really explain this data super well. If I use a quadratic function, I'm going to do a good job. The function is very close to the data. It doesn't have any extra power than it needs to explain this data. If I take like a high polynomial function here, it's going to actually do even better. If you look, the line is touching tons of points, right? So it's really good at explaining this data, but it's probably not going to be good at explaining unseen instances, as it were, because it's going to sort of wobble out beyond the edges. So that's overfitting. Our model's too powerful for the data that we have. And that leads to bad generalization power. So when we think about linear classifiers, or generally any classifier or any machine learning algorithm, we think about it in two terms, or I do, and it's common to think about it this way. Our loss term. How do we define a loss for an instance? Cross entropy, log loss, hinge loss, things like that. What do we want the classifier to do? And then a regularizer term here, omega, which bounds the capacity of the model in some way. We want to sort of make sure that the model isn't too powerful so that it just overfits the data, it just memorizes the data, as it were. Now, there's lots of different ways of doing this. It turns out there's a couple broad sword, techniques that will work pretty well. And the first one is the most common, which is simply the norm of the vector. You minimize the norm of the vector, right? And so this is kind of like the max margin intuition here, that all else being equal, try to keep our weight vectors as small as possible. Because of course, I can just take a weight vector and find one feature that's true for one instance and put a ton of weight on that feature. Just give it an infinity weight, right? And then I'll explain that instance. I'll get that instance correct. But that's not useful. All that's good at is explaining that instance. I want just enough mass on that weight so that I get that instance correctly, but I'm not sort of pushing the model too far just to explain an outlier or something like that. And that's what a Gaussian prior, an L2 regularizer, as we call them, will do. We also look at L1, which is just the sum of the absolute values of the parameters. Actually, the nice thing about this one is it promotes sparse weights. So set properly, you're going to get a lot of zero weights. And there's good reasons to do this. It makes the computation easier. If you zero out a bunch of weights, then your dot products are smaller. And sometimes we're talking about dot products with millions of features. So this can work well for computation. But the intuition here is some kind of like minimum description length principle. All else being equal, the description that's shortest is better, right? Or the simplest explanation is the best explanation. And by zeroing out a bunch of features, we're throwing away a bunch of things we don't need in order to make a prediction. Okay, so when we have a regularizer like this, how does it change our optimization? Well, it's just another term, right? So let's look at logistic regression. Let's say I put that regularizer in here. I've already computed my gradient for logistic regression as before. The gradient of this regularizer is quite simple. It's just, this is an L2 regularizer. It's just lambda W. Now I just add that to my gradient and I go. It doesn't change my optimization. I just have like a little bit extra math to do as well. And that's true also for support vector machines. So here is the general way we think of classifiers. We have a loss function and a regularizer. Support vector machines uses the hinge loss as its loss function. And in support vector machines, the regularizer is already baked in. It was part of the original optimization. So maximizing the margin is like a regularization technique already. So that regularizer is there. So that's the SVM optimization. So it's already in that form. It already has a regularizer. Let's look at the difference between the two. SVMs is a hinge loss, which is like this. Logistic regression, it has a log loss like this, and you can sort of rewrite it to be just filling in the formulas here. Basically, we want the probability of all the labels, including the incorrect labels, to be lower than the probability of the true label. And this is what we talk about soft margin. We're not actually forcing a margin. We're not saying that we need to classify it by a certain margin. We're saying push the weight or push the probability of incorrect labels as small as possible and the probability of the true label as high as possible. That's what logistic regression is doing. And if you think about the probabilities, you're creating a margin that way. And if you could truly separate the data, what you'd end up doing is putting all the weight or all the probability mass on the true label. And it would have a probability of 1, and the rest of them would have probabilities of 0. So margin is kind of already baked in to logistic regression, as it was just in the way that log loss works, which is nice, which is also why logistic regression is kind of the standard linear classifier that we use nowadays, including in neural networks. It's very powerful, very simple, but very powerful. I probably don't have to say a lot here. Loss functions are something the community spent a lot of time on, thinking about, how can we design these for different problems so that it actually represents, what we care about. It has to have certain things like continuous, it has to be differentiable so that we can run these kinds of gradient-based algorithms. But, I think it's very task-specific, and you can get more and more complex loss functions if you desire. Okay, I'm going to end there. How am I doing on time? Perfect. That is linear classifiers. So this was 2/3 of the lecture, and I think I've been exactly 2 hours, so I kept my word on that side here. I can't cover everything, obviously. We're talking about 150 years of or more of work. And actually, no one can really cover it, but Andre Martins has some great slides that go into more details as well. You can jump into there. That's one reference, and he's got other references in there, but take a look at that if you're interested. But now I want to get along to neural networks. The thing that we use nowadays for almost all classifiers. So, a reminder. This was linear classifiers. We had this was phi of x, right? We had some handcrafted features that we defined. We put them in, and then these are our y's, right? The scores of either the dog prediction or the cat prediction, right? And these connections here, and how we optimized it, that was perceptron, logistic regression, SVMs. But that was the linear classifier. As I mentioned earlier, we can rewrite this linear classifier as a matrix computation. We have a weight matrix now. We're going to call it W. Every row of that matrix is a weight vector for a single output. Phi of x transposed is just the normal phi of x. We're just transposing it so we can do the matrix computation. And then our bias terms b of y. If you remember, these are just extra weights that will tell us how likely, all else being equal, a particular output is, like a topic or spam or something like that. I'm going to do a little bit of a notational rewrite here and just say, well, actually, our inputs are x. So before I used to say, well, an input x is a sentence, and phi of x converts that input to a vector, a real valued vector. Now I'm just going to assume x is a real valued vector. And to be honest, I'm just doing that to make the notation a little bit easier to read. It also makes it a bit more standard with how neural networks are taught. But you can kind of just assume now that as input, we don't just get a sentence or a document, but we get some real valued vector for that sentence or document. And I'll show you how neural networks can kind of just make that easy, and we can learn that as part of our optimization as well. But just to be, a little bit explicit here, why is this a linear classifier? Well, let me just give you an example here. We have 3 labels, 1, 2, 3. So we have 3 weight vectors. So we have, y1, y2, y3 as our output labels. They have these weights, 1, 2, 3, 1, 2, 3, 1, 2, 3, and there's a subscript that indicates which label it is. It's the label 1, 2, 3, and we have an input x. I make my weight matrix here, where I just put the weight vectors on each row. I transpose my input. X, by definition, actually is the transposed input already, so it doesn't really matter. And then I have my bias terms. So if I do this matrix multiplication, I'm just going to write it out entirely. I get weight 1 times x1 plus weight 2 times x2 plus weight 3 times x3 for the first label. That's my first row, which is now just a scalar, a single value. And I do it again for the second row and the third row, and this is what I get. I'm going to add my bias term in, just bring that in to the matrix, and then I'm going to rewrite this part here as a dot product, because that's all it is, right? And I get W1x, W2x, W3x. These are the linear scores. So this is the linear classifier as before, and that's the outputs y1, y2, y3, or at least the scores of those outputs. So we're often going to think about y's now as being scores of those labels. And so this is a linear classifier. If I find just take the one here that has the highest score, that's my label. So this is the equivalence here between the two. All right, on to neural networks. Okay, so what is a neural network? I'm sure you've all seen images like this. There's kind of a few different concepts that are important to know. There is the output layer. I'll talk about that in a bit, but we've talked about it a lot already. These are the output labels, or the scores of those labels, right? What is the score of an image being a dog? What is the score of a email being spam or not? The input layer is X. That's X at this point. We're just going to assume we have some input layer X. Before we had this by defining these feature vectors, these feature representations. Now we're just going to get X. So that's something we've seen before. These are the hidden layers. So every sort of vector here of values, every single one of these nodes is a scalar. We call those nodes or those scalars neurons. This is what they call them in the literature. There's connections between neurons. This is where we start to get into neural networks and its connection to neurology. But a group at a particular time step is called a hidden layer. And we can see that there's these connections between layers. So kind of a fundamental concept that's, it doesn't have to be true, but it's true of neural networks as we typically implement them, is there's not a time series, but a sequence of computations that are happening between hidden layers. So information is flowing from one layer to the next, to the next, to a final layer. So we only have connections from a layer to the layer adjacent to it, behind it. This makes computation easy. There's nothing that says we can't have connections from here to here, and then actually in some neural networks, that's true. There's things like residuals, stuff like that make those connections. But let's just assume that that's not the case. This is an example of a fully connected network. A lot of the networks that we use in practice are fully connected. What we mean by that is that every neuron, so this neuron up here in this layer, it is a function of every neuron in the layer before it. So we compute the value here. Remember, these are just scalars. These are real values. We compute this value here as some function over these values here. And we call it fully connected. Again, it doesn't have to be like that. There might be problem-specific reasons. You might want to have different connections, maybe even computational reasons. You might want to have different connections. And people have looked at it in the past. But let's just assume it's fully connected. Fully connected neural networks, feed-forward neural networks, multi-layer perceptrons, these sorts of things go under many different names, but they are kind of a core building block of all the neural networks that you might use today. Okay, so we've talked about inputs and outputs before. I'm going to get back to them in the context of neural networks. Let's talk about these hidden layers. This is the kind of thing that makes neural networks different, right? I'm going to define these vectors h of I, right? So this is h of I. We graphically represent them as, nodes here, scalars, but mathematically we think of them as a vector. This is just a vector of numbers, right? I'm going to call that h of I to represent that vector for the ith hidden state. So we have so many hidden states, h of I is the ith one, and has some dimension, whatever that dimension is. We're going to say h of I is a function of I, so we'll talk about that in a second, of this linear classifier. Right? It's not a classifier here, it's a linear transformation, actually. We're going to take the parameters, the matrix, weight matrix for that hidden state. The hidden state are this vector here from the previous state, pass it through that linear transformation, add some bias term if you want, and then you're going to get a vector. Depending on the size of this matrix, that'll determine the size of the vector you're going to get on the output. And we pass it through what's called an activation function. So f here is a way of maybe adding some nonlinearity or adding other properties that we might want to the data. But even though I might say classifier here, really this is a linear transformation where we're moving from one representation through a linear transformation to another representation, and then we'll add f of I to this and potentially get a nonlinear representation. So what are activation functions? Again, like many things I talk about here, there's a whole field where people have studied this, and there's tons out there. Here's a few that are commonly used. I would say sigmoid is very common. This is a squashing function. One advantage of sigmoid, it'll take any value, so whatever x is, or z in this case, here, and it'll squash it between 0 and 1. And that's useful, particularly from a computation numerical stability point of view, because if we're learning our weights and we're passing them through all these layers, we might get sort of numeric overflow or things like that. So essentially, this squashes those values down to a nice small space, and it makes things a lot more stable. Sometimes it can increase prediction power as well. Rectified linear unit is essentially 0 if z is less than 0 and z otherwise. It's essentially like a gate where you pass the true value if it's greater than some threshold, otherwise you just blank it out, 0. These and versions of rectified linear units are all over modern neural networks. They have like different parameters or different ways of seeing them, but basically that's it. So these are the activation functions that we sometimes use. Okay, so that's hidden layers. I'm going to go through a full example to tie it together in a bit. Let me look at the output layer. The output layer is the first part of the lecture, right? We have, let's say, h final minus 1. So the last hidden state. That's our input vector phi of x. We're going to get it from a neural network. That's phi of x as we had before. These are our parameters that we had before. Now it's in matrix form, but I showed you before that's equivalent, and maybe a bias term. We weren't using that before, but we'll keep it here. These y's here, these are the scores, right? So we run the linear classifier here, and we get the score. And before, we would just take the argmax of that score. We would do a softmax transformation if we were doing logistic regression. We would optimize log loss, whatever that might be. Turns out we're doing the exact same thing here, right? We get these scores, we use that for prediction, or we sometimes call logit of y to be the score of a particular label. We do a softmax transformation here. This is identical to what we did for logistic regression. We get a few scores for output labels, pass it through the softmax transformation, exponentiate, normalize. We get a probability distribution, but we could use anything we want there. But then we also use log loss, our cross entropy, right? We've computed all this stuff to the end. We have a loss function, which is based on the scores of the predicted labels relative to the true labels. We optimize that the same way we did before. Now, optimization is going to be a lot trickier here, but in theory, that's all we're doing. We're just computing some scores for labels, and we're defining a loss function over those scores, and we're optimizing. Let me not talk about the input layer in a sec. Just assume that that's fixed. Just to kind of like make it very transparent what's happening here, let me just give you a small example. Our x is a vector of size 2, dimension 2. The first hidden layer here is going to be tan h. That's going to be our activation function. Doesn't matter what that is. We have the parameters of that layer, W, matrix W, and the bias term. And then the last layer, so this is a single hidden layer here. The last term, or the output, we have two labels. We're going to define that as W prime, B of prime, right? So this is the last layer linear transformation with certain parameters. And then we're basically going to say, okay, our loss function is going to be the log loss, which is the exponentiated function here. And just to make that explicit, what we're going to do is get scores y, scores y1. We're going to pass it through the softmax layer here, which is just exponentiate y0, take the normalization, exponentiate y1, take the normalization. We'll get our two probabilities here, and then we're just going to do logistic regression. We're going to do log loss over that. That's all it is. And internally, these are just the computations. I'm not going to go through them, but if you want to take a look, you can just see on a very small example like what the exact computation might be to get to the end. Okay, so let's again, like I said, let's assume that the input is fixed. The input is actually a can of worms that I'm going to get to in a second. We assume that the input is fixed. We have some outputs y. We have these hidden layers. The parameters of the hidden layers now, which are the linear transformation layers, the matrix W and the bias term B, plus, that's not a parameter, that's just a definition, the activation function. These are the model parameters. So this is what we have to learn in a neural network. We have to learn the W's, the weight vectors and the bias terms for every hidden layer, including the last output layer. That's the goal here. And as I said, the loss function is the same as before. Let's say logistic regression, any loss function you want at the last layer. You're going to compute it with respect to the last layer, but we need to learn all these parameters here. So these hidden layers make the model non-convex, so we don't have a single global minimum right now. It's still differentiable, so we can still optimize it, but we're only guaranteed now to find a local optimum, some stationary point. We're not guaranteed to find a global minimum, which turns out in practice is not that big a deal. I think it's something people worried about for a long time, that we were only optimizing things that we could guarantee we were going to get to the optimal output. But even though these things are very nonlinear, it turns out in practice there's lots of good local optima. So you're going to get to some local optima in the function, but there's lots of good ones. So we usually get to a pretty good place after all. However, and we're going to use gradient descent. We're going to take the gradient of these functions as we did before. We're going to take that gradient and update the weights. So all of that is identical to linear classifiers. Just computing that gradient, these hidden layers, makes it a lot trickier. It's a bit harder. I'm going to go through an example here. It's something that is one of these things that you always have to go back and reference. I think nobody just kind of knows intuitively. So we'll look at an example, go back. It's important you understand how it works, but it's not going to be something I think that, or at least for me personally, that I just do without hitting a reference. And nowadays, all of these modern frameworks do this kind of optimization for you anyways. But it's good to know it. Okay, so we need to compute the gradient of our loss function with respect to our parameters W, remembering that the gradient is just the vector of partial derivatives with respect to each parameter by itself. This was the feature weights for linear classifier for neural networks. It's the set of weights for hidden layers, right? These weight matrices that transform the hidden layers. We're going to use the chain rule in backpropagation, which is the way we're going to optimize this. Chain rule says that if z is a function of y and y is a function of x, then the derivative of z with respect to x, or the gradient, if these are vectors, is the derivative of z with respect to y the derivative of y with respect to x. So that's, a known rule. Just to give you an example, let's say L is a function of z. So maybe z is the score of some output, and we're taking some log loss there or something like that. And z is the function of x and y. We want to compute the gradient of L. We need to compute the partial derivatives of z, x, and y. Those are the parameters, or those are the values of the model. According to the chain rule, dl of z is easy because L is directly dependent on z. But then we're going to use the chain rule to say the derivative of L with respect to x is L with respect to z, z with respect to x, and the same for y. So we're going to use the chain rule to find the different partial derivatives that we're going to need to optimize this. Okay, so here is a very small toy example to kind of see this. So in this model, we have an input x, that's fixed. Those aren't weights. Those are just values. Output y with a loss function that I've just defined here. So y is the true label, y prime is a predicted label. We just subtract them and take a square. So this is kind of a squared error type of loss. And we have one hidden layer here. And that hidden layer, those values, are determined by weights 1, 2, 3, and 4. So this is our weight matrix at the first layer. And then the final layer, y, is determined by U1 and U2. So these are also weights. So purple nodes are the weights of the model. And it's all, every layer now is just a linear transformation. I don't even have activation functions at this point to make it simple. Activation functions make the gradients a little bit more complicated, but don't worry about that now. So this is how you compute it. What we want, the learnable parameters of this model, are the purple circles here. So in order to take the gradient, these are the values we need. We need the gradient of the loss, of the partial derivative of the loss with respect to U1 and U2, W1, W2, W3, W4. That's the gradient that we need right now. To do this, the first thing I'm going to do is create a table of base derivatives. So these are simple things that I can compute by just looking at the structure itself. For instance, the derivative of L with respect to y is simply 2y minus y prime, right? I just move the 2 in, basic derivative. The derivative of y with respect to h1, right? That's that function here. So y is computed via this function here. So it's u1. This zeroes out because h1's not there. And u1 times h1, the derivative with respect to h1 is simply u1. And I just keep doing that for every layer, right? These are simple things that I compute. I don't have to use the chain rule or anything like that to compute. It's just, I can read it off the table in some ways. Like the derivative of h2 with respect to w3, h2 is computed by this function here. With respect to w3, well, w3 is not here, that zeroes out, and then it's just x3. So that's how I get that there. Now, to compute these, I need to start using the chain rule. So what I can do is say the derivative of L with respect to u1. So let's say I want to compute this value here. I'll use the chain rule and say it's L with respect to y, y with respect to u1. I know those two derivatives. I can look those up in my table, and I get this function here. So we can use the chain rule, go through the network, and get, basically analytically write out what are the derivatives, what are the partial derivatives for every single variable that we care about. Now we get to backpropagation. So how do we compute that in a real life example? So the way we do this, there's typically two passes. We're going to compute a forward pass. We're going to take an instance. We're going to compute the value at all the hidden layers and the output layers. That's going to be our forward pass. And then we're going to use those values and start moving backwards across the neural network to the input, slowly computing the partial derivatives at every node that we need. And if the network is big, we need to be smart about how we do this, cache values, do some dynamic programming. There's a lot of, this is what, again, modern toolboxes do for us, all of that sort of in there, so that we can do it efficiently. But this is small, so we're just kind of do it brute force. So let's take a look. So let's say I get an instance X, which has these values here. First, I'm just going to run it through the neural network and get this value here, right? So at this point in time, my weight vectors, I also have some weight vectors, right? So at any point in time, I know what my W1, W2, W3, W4, U1, and U2 are. These are my W's, these are my U's. I get an X, I run that computation through, and at the output, I get a -1. That's the score at the last. And you can just do this yourself. It's not hard. Get the -1. Now let's say my true label is 1, right? So I've done my forward pass. I've gotten what the model predicts, which is -1. But let's say the true label y is 1. And I've defined this loss function as y minus y prime squared. And this is the derivative over here. Let's start backpropagating values. Let's start computing some partial derivatives that we need. Well, the first is L with respect to y. I know y prime now. I computed it. That was my forward pass, what the model thinks the true y is. And I know my true y. So I compute that. 1 minus minus 1 is 2, times 2 is 4. So I start passing that back through the network. Now let's say I want to compute the derivative of my loss function with respect to u1. Well, I've already figured out using my lookup table that I can use the chain rule. It's L with respect to y with respect to u1. I've already just computed this, right? It was 4 here, so I'm going to plug that in. I have my lookup table here that tells me this partial derivative is h1. I computed h1 in my forward pass. I put it in here. I get 16. All good. Now let's say I want to do h1, the derivative of h1, or of L with respect to h1. Again, using the chain rule, L with respect to y with respect to h1, L with respect to y. I know I'm propagating that information backwards. For y with respect to h1 is u1. u1 is 0.5 over here. Boof, 2. I'm all set. I propagate that through again. Now what I want is w1. w1 can be L with respect to h1, h1 with respect to w1. I've already computed L with respect to h1 over here. It is 2, so I'm going to put that in. This is why I'm back propagating that information. H1 with respect to w1, h1 with respect to w1, where is that? I think that's just x1. Oh yeah, sorry, it is. x1 here, that's what that is. If we take our lookup table on the last slide, x1 is 2, put that in, I get 4. So I'm not going to do every value here, but we've computed the partial derivative of the loss function with respect to w1 is 4, and u1 is 16. We can do it for this value, this value, this value, this value, and we get our gradient. And that's our gradient. And then we just run gradient descent like before. No problems there. And this is backpropagation. That's a general intuition. We compute the values based on the current parameters and inputs now, start at the end, and start backpropagating derivatives, gradients, so we get all the variables that we need. Okay. So if we assumed that x was given, the inputs were given, that we just know them from somewhere, you already have enough. Well, we've done the math that we need to train a simple neural network at this point. But where do these inputs come from? We talk about x being a high-dimensional feature representation. Again, we could just do what we did in linear classifiers. We could just define a bunch of feature functions and create a vector that way. But you don't really need to do it. There's better ways of doing this here. And in particular, we should lean into the fact that neural networks are really good at dealing with real-valued numbers, dense vectors. Modern architectures like GPUs are really fast with dense, large vectors and matrix computation. So why don't we just embrace the vector and learn real-valued representations? Okay, so here's an example. Okay, so let's say we have the word work, and I want to know, is it a verb or a noun? So this would be like, the teacher went to work, which is a verb, and the job was tough work. Oh no, that's also a verb. The work is hard, so a noun, something like that. And we want to classify it with one of those two layers. The input's a word. is going to be some dimension d, and we assume that we have a finite vocabulary. So our inputs, we know the set of words that we might have. This is kind of an assumption that we're making now with neural networks. There's ways around it, but it's a good assumption to have. So what we want to do, and this is an important concept, is what we need to make a classification like that is we need what's called a lookup table, an embedding layer. Essentially, this is a table where you get a new word as an input, like work. That indexes into a vector over here. So work will pick up this vector here. We'll pull that out and we'll run it through the neural network. So this is an important concept to understand. We have this vocabulary. That vocabulary, every word in that vocabulary has a vector associated with it. And at inference time, we take the words that are in our input, we look up those vectors, and we pass them through the neural network. Okay, so where does this come from? What types are there? Static embedding layer, so this table here, we can say that, well, this just exists already. We learn it in a separate process, and once we learn it, it's fixed, right? So when we're optimizing the neural network, we're not optimizing this table at all. It's fixed. It's already static. I'm going to give you an example of that, particularly Word2Vec. That's a good example where we learn a representation of words, and then we just fix it forever. Dynamic, which is what we do nowadays, is we just say, like, well, these are just other parameters, other weights that we want to learn. So we want to learn this table as we learn the neural network. Now, it's a really big table, right? You're going to learn a vector for every single word in the language or all the languages together. So you're going to need a lot of data in order to make sure you learn that reliably. But nowadays, especially with large language models, we train these on the entire web, common crawls, huge amounts of books and everything like that. And so that is enough data to actually reliably learn these tables. So I'll talk about that in a second. People don't do it now, but there was a period where people tried to do a little bit of both, maybe have a static version and a little bit of the representation can be learned to make it more task specific. But I would say nowadays, we really do this mostly. But let's look at a static example. So Word2Vec, I think probably most people here have heard of Word2Vec. I want to kind of go over it because it's a seminal work in the field. So let's start with a corpus, C. This is a bunch of sentences, X1 through XC. Sentences have words X1 through XX. So our vocabulary is every single word in our corpus, right? So this is going to be our lookup table. Every word that is in the corpus, we want to learn a vector for that word. So the intuition behind Word2Vec is that a vector for a word or a representation of a word should be good at predicting which words exist around it, right? So if I think about the word sailor, sea, boat, fishing, stuff like that, these are the words that commonly happen around sailor, and a representation of that word sailor, it should be good at predicting the words that come around it. So maybe the word mountain would have a low probability for the word sailor because it doesn't really happen around it. So there's kind of two things happening here as well. So what they did was they defined two vectors per word, x and x prime. This is the word. This is what we care about. When the word is at the focus and we're thinking about that word, can it predict its context words, the words around it? X prime is a representation of that word, maybe for another instance where that word is a context word itself. So maybe one case sailor is the focus word and I'm trying to predict that ocean and fishing are around it. In another case, fishing is the focus word and it's trying to predict sailor. And we'll have different representations of sailor depending on whether it's the focus word or the context word. So the way they do that is they say, okay, here's the loss. For every single sentence in the corpus, for every word in the sentence, define some window, C, and this says how many words to the left and words to the right of the word that I'm looking at right now do I want to consider as my context. So minus C plus C, and we don't care about the case where C equals 0 because that's my focus word as it is. I want to optimize the probability that I can predict the word in the context given my focus word, right? So from sailor, I can predict ocean. I want to maximize that probability. We will rewrite that, and we take these vectors to represent the words, and we just take our standard softmax transformation and say this is a normalized exponentiated function, the dot product between xj, which is sailor, x prime j plus k, which is the representation of ocean, let's say. So that score, divided by a normalization term. And here we're actually summing over every single word in the corpus. So this is an example where words is a class. So we're saying predict a word. That's your class, which we tend to think, we didn't really think of classification as that. We think more like add a topic to a document or something like that. But predicting a word is a class. Of course, we have the problem here that the size, the vocabulary size is quite big. So this sum can be quite hard to compute. But this is the basic part of Word2Vec. To give you an example of how that might work, let's say we have the quick brown fox jumps, right? One example, brown might be the focus word, and so the quick fox jumps are the context words. But for that sentence, we're going to sort of run a window over that sentence. The word in blue is the focus word, and we're going to create training instances of this example. Focus word, context word, focus word, context word, move over. Focus word, context word, focus word, context word, move over. And we're going to keep doing this, right? So we have a bunch of pairs of focus words on the left and words that are in their context. And this is going to be our training set that we're going to use to optimize this function. So focus representation will be x of j, context representation will be x prime of j plus k. So that's actually one of the insights of Word2Vec is like I can learn representations for words just by having a corpus of data, by having the web, huge amounts of data. So even though my vocabulary is huge, I can get tons of data to learn that and reliably learn those vectors. So rewriting the equation a little bit, we're basically saying we want to maximize the score between a word and a true context word, and basically take away scores from a word and some random other words. So some word that is not in its context, or maybe not in the context, right? This is a sum over all the words in the vocabulary. Again, this sum is huge. So one thing we often do is say like, well, we're going to define vocabulary of S, which is a subset of the whole vocabulary, particularly much smaller. And we're only going to do the sum over that. So this is a way of approximating the normalization term with just a much smaller, easier to compute size of outputs. And in fact, we often just use one word. We just sample randomly a single word in here for the optimization. And it turns out that that works pretty well. And of course, it's much easier to compute. So this is a trick of how to get Word2Vec running computationally well. So we optimize this. It's differentiable. We'll use gradient-based techniques as before. I'm not going to do it, but you can take the gradient of this. You just run it again, run it through the pipeline. That's easy. At the end, these x of i's, the representation of the word as a focus word, that's our final embedding. That's what's going to be in our lookup table. And about 10 years ago, there was a lot of fun facts around that we could do like a little arithmetic with these vectors and learn interesting things that just kind of fell out of the data. It was more anecdotal examples of trying to prove that, at least qualitatively, these vectors were learning semantic or even pragmatic relationships between things. Okay, so embeddings in language models, Word2Vec itself is an example of a language model. I can predict a word, a context word from a focus word. That's not what we use when we think of language models, but it is a type of language model. Nowadays, of course, pre-trained contextual language models went much further. Not only did they learn these embeddings, they also learned specific tasks. And nowadays, GPT, Claude, Gemini, whatever. These are kind of the natural progression of everything that's happened here. And this really transformed the field, right? Now this forms the basis of, a ton of research, but also from a commercial side, what we do. I'm not going to cover any of these. You're probably anxious to get into this side over here in particular, but that's the next lectures. I want to kind of just get you the basics here, and then you can move on. All right, so getting back to neural network, I can learn this table here using Word2Vec. My embedding table, I use Word2Vec. And then I want to make this classification. I just pass, I get the word work training or inference time. I look it up in this table, plop it in here, and then I run my neural network. And that would be kind of a full end-to-end version of a feed-forward neural network. However, a lot of people pointed out that you don't have to learn the table offline beforehand. These can just be parameters, right? Anything can just be a parameter, can be a value that I can learn. And so what I can do here is say what we want, remember when we optimized this network before, these were the free parameters that I could optimize. Well, I can actually just add these gradients here. What are the values for x1, x2, x3, x4? Now I have to do it for every single word because these values are going to be different per word. So I have to do it for all the parameters in the lookup table. But I can just treat them as parameters. I can throw it into my gradient computation. I can run gradient descent, and now I'm learning the whole network entirely. The caveat there is that you have to have a lot of data to do it, which is why nowadays something like ChatGPT, which uses a transformer-based language model, it's trained on tons of data to predict the next word, because only then can you reliably learn these embedding tables. Okay, so I've kind of assumed with neural networks up until this point that I have a fixed length input, a single word. Someone gave me a word and I have to make a classification of it. Of course, in language processing, the things we tend to process, sentences, documents, are not fixed length. Sentences of different length, we want to generate sentences of different lengths, etc. So what do we do in that case, right? If I get a sentence like, the steak was cooked to perfection, I want to understand, were they trying to say something good or bad about that steak? So a couple very simple techniques to handle this is, we just truncate documents at some fixed length. So maybe I decide to say my fixed length is 4. Any sentence is longer than 4. I'm just going to ignore everything that happens after it. And then I've got a fixed length input. Essentially, 4 of these vectors, I can concatenate them together and pass that as my input. Another thing to do is to average these. So if I have something like the steak was cooked to perfection, I want a fixed length vector. Well, I can just average these and I'll get a single vector here. And there's some intuition that the average of all the vectors in a sentence represents that sentence. That's very akin to a bag of words representation we talked about at the beginning, right? Where we just sort of treat words independent of their position or anything like that, or of each other. And that's kind of a very similar approach, and it's very simple. But the more principled approaches, which we're going to talk about, are convolutional neural networks and recurrent neural networks. This is the subject of at least 1 or 2 lectures coming up, but let me talk about convolutional neural networks now. All right. So this is our input. We call this padding. Sometimes we add special tokens at the front and ends of our input just to sort of let the model know where in the sentence it might be. This is more an empirical trick than anything principled. We have something called a convolutional layer here. The idea here is we take an MLP. This is any neural network, a bunch of hidden layers, like the feed-forward dense neural networks we talked about before. It's just another word for it. This is a block here. Don't worry about what that is. You can define whatever it is. That MLP is going to sort of slide along the sentence, and it's going to take a fixed window of inputs into it. So here it's 3. So this MLP takes the first padding, and steak, passes those through, and creates a new vector representation of the sentence. And so we just kind of slide that along the input. And in this case here, because of the padding, we end up with a number of vectors actually equivalent in length to the original sentence. And no matter how long the sentence is, you can just do this and you'll get some new vectors. And then we do a pooling layer here. This is what's called average pooling or max pooling, but basically it's a way to sort of compress all of these into a single vector. Now this is better than averaging from the beginning, and the reason is that this representation here starts to become context dependent. By that I mean it's not just the representation of the in isolation, it's actually a representation of the between start of sentence and steak, right? So we start to get more context dependent representations of our words. So we're starting to blend that structure. We're moving away from bag of words and we're starting to sort of model that structure via these what are called filters ultimately, which are really just data transformers. So then when we average at this point, we're not just averaging words in isolation, we're averaging sort of these micro contextual representations of those words. And in practice, this can do a lot better. These MLPs are called filters. Based on history, filters are often seen as just ways of transforming the data from one state to a next, but it's really just a neural network. This is called the receptive field, which is the part of the input that those filters is going to be conditioned on. So this, let me just back up. So this is a convolutional neural network, a specific, very simple instance of one. It's a neural network architecture, slides over the input at some stride. Here it was stride 1, meaning it slid over every single word, but you can have larger strides if you want, for computational reasons, I suppose. The filter just transforms the data at every single point. Yeah, you can have filters per position, but really this neural network, this neural network, this neural network, this neural network, they're the same neural network. We have the same parameters. Usually that's a simplifying assumption that we don't have different neural networks per position, but you can if you want. And then the pooling layer is a way of going from a lot of vectors to a single vector. Average pooling is probably the most common. You just average those vectors. Max pooling, maybe you take the max value across those vectors for every single node, but yeah. Okay, so let's get into deep neural networks. So now you have a convolutional neural network. Well, what I can recognize is that if I have this convolutional layer and it creates a new set of contextual vectors that is the same size or same length as the original sentence, I could use that somehow. The simplest thing I can do is in my pooling layer, maybe I don't average them all. Maybe I don't flatten them all. Maybe I just average at the same receptive field that I had over my MLP, and I get a new representation here. Maybe I don't at all. Maybe there's no pooling layer here. But the idea is at the end of this convolutional block here, I get a set of vectors. I don't get a single vector at all. And then what I can do, depending on the size, and this is just something you can control with the architecture, is I can just start piecing these together. Convolutional block after convolutional block after convolutional block. Maybe they all have the same parameters, maybe they have different parameters. This is a choice we can make, but we can go arbitrarily deep. And this is where we get with large language models. When we talk about large language models, they're large on a couple dimensions, well actually a number of dimensions. One is the size of the hidden representations. So they're not 5, they're much, much bigger than that. But one dimension that they're definitely large on is the number of blocks or layers this way. And that's both in terms of how many of these we stack together, but how big each of these filters is. So we can sort of expand the capacity of the model by taking any one of these dimensions, the size of the hidden layers, the number of convolutional blocks we have, the size of the neural networks in these MLPs, and we can just keep making that bigger and bigger and bigger. And all we're doing is we're adding more parameters to the model, and the capacity of the model is getting really big. So you need tons of data, again, to learn that. But that is the trick. That is large language models. Now, they're not using this particular architecture here, but they're using those intuitions. You take a neural network architecture, transformers, you blow it out to be as big as possible, get tons of data to predict the next word, classification problem, and you go from there. And that is I would say in a nutshell, the kernel of what large language models is and what AI is today. Okay, good. I think I'm doing well. Actually, I think I have a bit of time. So neural network summary. Feed-forward neural networks, the thing I talked about at the beginning, also called multi-layer perceptrons. Basic networks, hidden layers, inputs, outputs, kind of the building blocks of a lot of what we do later. Right, we have hidden layers, neurons, output layers, input layers. For the input layer, static versus dynamic, do we just learn the input layer offline using something like Word2Vec, or do we learn it as part of the model? All of this can be trained with backpropagation, which is a little tricky, but it's you can even do it with automated tools nowadays. There's these questions around like, why should I use a neural network? I don't think I have to answer that anymore. They're really good, and I think we've all used tools out there that are extremely impressive. Where does a layer and network structure come from? 5 years ago, I would say this is like a big active area of research. Maybe you make task-specific structures, or maybe there's optimal structures like adding sparsity to the connections or things like that. And people, to be frank, people are still working on these kinds of techniques. But I will say it's kind of fallen down the totem pole in terms of priority. People tend to use transformers, and that's kind of become the standard structure. But I think in the future that will change. We're just sort of in the period now where that's the area that's fixed, and people are focusing more on optimizing around that structure. Hyperparameters are part of the structure, how big the input and hidden layers are. Deep learning is lots of layers. This is stuff I mentioned before. Okay, so if I'm just backing up here, and I want to say, like, what do I want you to take out of this lecture? There are really kind of four things happening, or four decisions that you have to make for classification, whether it's neural networks or linear classifiers or anything. First is, how do you represent your inputs, right? So we talked a lot about phi of x, handcrafted features. Word2Vec is another way of representing inputs, or just learning them, just learning those parameters in a neural network. The outputs, right? Well, usually our outputs are task specific. We know what we're trying to do. Label emails, label documents, machine translation, something like that. But what we have to decide is, what does that last layer look like? What are we optimizing for? What's the loss function? And I talked about log loss, hinge loss, perceptron, sort of standard things there. The model, which is all the bits in between. What assumptions do we make? Sometimes the loss dictates exactly what model you're talking about, but then of course in the neural network space, do we do something like feed-forward neural networks? Do we do a convolutional neural network, RNNs, we're going to talk about later. So the actual function of the model. And there, it's not just the structure, it's also the assumptions that we're making about the input and how it's going to play with that model. For instance, like bag of words, feature representations. And then the loss function on top of all of that. How do you define it? How do you take the gradient? And how do you optimize? Do you just do simple gradient descent? Do you have to use something like backpropagation to get those gradients and move from there? But ultimately, if you get the loss function, you can compute a gradient, you can optimize. That's the core. Main point in words, I'm not going to go over that again. There's some references, and that's it. So I think I'm going to end there. Thanks. We do have time.
So I have two questions.
Yeah.
One's about the Word2Vec. And if I understood correctly, after you train, then you have a one-to-one mapping for each score.
Yeah.
To a vector.
That's right.
So what do you do if you get an train?
Yeah, so you do something a little bit like what we did for the feature representations in linear classifiers. We define something as the unknown word, right? And what we'll do during training is maybe we'll use something like frequency. A word has to occur in the training data more than twice for it to live in this lookup table. All other words we'll say are unknown, right? And we'll put the unknown word to that. So that way, if we see a new word at test time, we just give it that vector. That's kind of the standard trick, yeah.
Then the second question is a bit more, maybe I missed something there.
Yep.
About the convolution. And then you put them forward in a way to be more flexible in the length
Yep.
which you give. But I'm having hard to understand how this is the case, especially here.
Yeah.
You have this little sentence.
Mm-hmm.
I don't know what, five words.
Yeah.
And what I'm gonna do in my next example has 6 words. I don't see how this can.
Well, let's think about actually the opposite, where the sentence was really, the steak was cooked, right? So that's a real sentence, right? So a different size input. What we're going to have here is this end of sentence is going to go up here. So to perfection just doesn't exist in that example. The end of sentence is going to go up here. I'm only going to run these MLPs, right? So this part's not fixed. This part is dependent on the number of words that we have.
You're gonna fix the number of MLPs, and then you're gonna pad with zeros the rest when you write the workflow list.
No, actually there's no point in here where we have to assume anything. Like the number of MLPs is not fixed. If I get a shorter sentence, I'm just going to use less MLPs. I'm going to get less vectors over here. And then my pooling layer, it doesn't matter, right? It doesn't really matter. So this is going to scale with the size of the sentence, right? This representation here, if I get more words in the sentence, I'm going to get more vectors here. That's why we still need this pooling layer. At the end, at some point, we need to project it down.
Yeah, you need the global reduction.
Yeah.
The average.
Yeah.
Thank you.
I saw it, yeah. I think there might be a microphone now, yeah.
Thank you for the nice presentation. My question is, you talked about static and dynamic layers. In practice, when we say we take a model, let's say BERT or Word2Vec maybe even, and we fine-tune it on our data set,
Yeah.
what do we do in practice? Do we train some of the latest layers, or do we start from there and train further layers?
So I think it depends. Like, for instance, if you took Hugging Face and you took like a pre-trained BERT model, and I have some classifier, and then I fine-tuned it, you're training everything. You're training all the layers. I mean, that's kind of the default case. You don't have to, right? And there's techniques like adapters, where you're only training variables that transform the fixed parts of the layers. So if you're doing something like, I mean, obviously I don't know what's under the hood at OpenAI, but if I click the train function on ChatGPT or something like that, I'm not training all those parameters. First of all, my data is probably not big enough to be useful. So you're training like adapters, which are a smaller amount of parameters that are being learned on top of the fixed set of parameters. Now, a simple way to do it is what you said. Like, just learn the last layer. So fix it. Let's say I have like, thousands of layers or whatever, and all these parameters, I don't have enough data. Well, I'm just going to do the last layer, just the prediction layer. And that's kind of akin to trying to take a model that's generalized and project it a little bit into a task-specific place. But yeah.
Hello. Could you talk about the concept of overfitting in neural networks? In those traditional models like logistic regression and SVMs, you have a small number of parameters,
Yeah.
but in neural networks we go to millions, trillions, and so on.
Yeah.
And if you're familiar with the concept of double descent, and if you could kind of give me your opinion on that.
So actually, I'm not familiar with double descent. I don't know what that is. But obviously, it's almost like a paradox a little bit that we increase the capacity of these models and they generalize better. And actually, when feed-forward neural networks first came on the NLP space, so before pre-trained models and everything like that, people were using feed-forward neural networks for sentiment analysis or things like that. And they were getting better results, which is counterintuitive to all learning theory because we're taking the same amount of data and we're blowing out the parameter space, so we should be overfitting. So why?
That's the concept of double descent. Basically,
Yeah.
at some point it starts to overfit, and from after a certain point, it starts to generalize.
So it's a generalized well, yeah. And I know people have studied this. I mean, obviously in pre-trained models, you have so much data that extra capacity is not really a problem, and then it's just kind of moving around a little bit in that space. But why is that happening? It's hard to say. I mean, there's some literature, like essentially around the fact that like neural networks are learning like small sort of, hyperspaces or whatever. Each space is specific to a category, and at the beginning it's very noisy, but it gets sort of cleaned up over time. I think the verdict is still out on that. Yeah.
I have, I have one question as well. So at one of the last slides, you proposed a question: why should someone use a neural network, right?
Yeah.
And I think it's also equally important or interesting to ask the question: why should someone not use a neural network? If you think, for example, from the perspective of interpretability or explainability, because to my understanding, like by seeing all this mess of all these parameters and these feed-forward layers, you basically lose the explanation of why exactly you get the output that you get. So my question to you is, how do you maybe see the field moving towards different architectures that may enable this kind of explainability or interpretability, and what maybe do you kind of envision as like a post-transformer era, like the next kind of step towards, or like the next kind of advancement?
Yeah. That's a good question. I don't have a great answer. I will say, obviously, that's a problem. And, a lot of solutions, particularly post hoc solutions, first there were solutions like probing that probe different layers for values. Now we have things like critics, so large language models that are the explainers themselves of other large language models, including themselves. We call those post hoc kind of interpretability and explainability techniques. Obviously, that's a problem, right? That is, I said those solutions are suboptimal because they're looking essentially outside the box and trying to predict what happened inside the box, but we don't know, right, that's the case. I think the most interesting work that's been done, or at least the work that I trust the most, would be cases where you sort of have hard layers of your neural network. So a good example might be something like I want to summarize a document, right? And, I could just take ChatGPT and I could say, okay, here's a document, write a summary for me. And I get a summary out, right? And then I could ask another large language model, like, why did it give you that? Why did it pick that summary? And it might say like, well, this sentence here was based on the information over here or something like that. That's all kind of post hoc stuff. But if I do it in a way where I have a model that sort of stages it, so first it hard selects the evidence I'm going to talk about and then summarizes from that, so you have multiple stages, you start to get things like information provenance and tracing in the system. And you still can't guarantee much, right? Because obviously I select some information and I generate from that information. Maybe I'm hallucinating on the top of that. But you are sort of putting a hard border here that you're now narrowing the scope of the predictive part of the model to a certain subset of the input. So this is like a type of masking or something like that you might have in place. And I might be wrong here, but at least in what's visible now, I would say that's kind of the most reliable way of doing it. And I think from a computation perspective, we know how to do it. It's more just making it common, yeah.
Thank you very much. We have to stop.
Okay. Thanks, everybody. I got a present. All right.
Thank you so much.